Right now, you are surrounded by something. Something is passing through the walls, through the floor, through your body, through the atoms that make up your hand, your brain, every cell you have ever been made of. And you cannot feel it. You cannot see it. You cannot smell it, touch it, measure it, or interact with it in any way your senses understand. And here is the part that should genuinely stop you cold. That invisible something is not a trace amount. It is not a background whisper. It is not a fringe phenomenon at the edge of physics. Whatever is passing through you right now, whatever surrounds you and floods through you and fills every cubic centimeter of the space you occupy, that stuff makes up nearly 95% of everything that exists. Everything you have ever seen, every star, every planet, every galaxy, every person, every ocean, every mountain, every atom of everything that has ever been built or grown or touched or loved, all of that, all of it, constitutes roughly 5% of the universe. The remaining 95% is something else entirely, something we have no name for, no theory that fully captures, and no detector sensitive enough to confirm. And the deepest, most quietly disturbing part of this is not that the universe is hiding something from us. It is that the universe may be hiding most of itself from us, and doing so using a method so elegant, so total, so structurally embedded in the nature of reality that we are not even sure we have the right conceptual tools to think about it yet. If you are new here, welcome to Silent Cosmos. Get comfortable, settle in somewhere dark and quiet, and stay until the end, because what we are going to work through tonight is not a mystery at the edges of science. Part 1. The inventory of everything. Let us start with what we know. Let us build the picture carefully from the ground up, because the only way the 95% number lands with its full weight is if you first understand what the 5% actually is. Everything you have ever seen with your eyes is made of atoms. Atoms are made of electrons orbiting a nucleus. The nucleus is made of protons and neutrons. Protons and neutrons are made of quarks. Quarks, electrons, and a small collection of other fundamental particles are what the standard model of particle physics describes with extraordinary mathematical precision. This is the world we know. This is the physics that powers nuclear reactors, explains chemical bonds, describes the behavior of every substance you have ever encountered. This is baryonic matter. Named for baryons, the class of particles that includes protons and neutrons, baryonic matter is everything we are made of and everything we can directly observe. When you look up at the night sky, every star you can see is baryonic matter burning, fusing hydrogen into helium, releasing energy in the form of light. The moon is baryonic matter, reflecting that light. The atmosphere you breathe through is baryonic matter. The ground beneath you is baryonic matter. Your body is baryonic matter. The coffee getting cold on your desk is baryonic matter. Everything in your field of view, every object you have ever touched, is made of the stuff described in the periodic table, which is itself just a catalogue of different configurations of quarks and electrons arranged into atoms. This is the entire visible universe, and according to our best current measurements refined over decades of increasingly sophisticated observation with the Planck satellite, the Dark Energy Spectroscopic Instrument, the Atacama Cosmology Telescope, and dozens of other instruments, this entire visible universe, every star and planet and galaxy and nebula and black hole and molecule and gas cloud you could ever point a telescope at, constitutes approximately 4.9% of the total mass energy content of the cosmos. Call it 5%. Round it generously in the direction of familiarity. Even so, we are describing a universe in which nearly everything is something we have never seen, never touched, and in many ways, never adequately theorized. That leaves 95% unaccounted for. 27% roughly is something called dark matter. 68% roughly is something called dark energy. Both names are placeholders. Both names mean, in the most honest scientific translation available, we detected a gravitational or cosmological effect that required this thing to exist, but we have no idea what the thing actually is. Dark is not a description of their color, which would be meaningless since they have no electromagnetic properties we can detect. Dark is a description of our ignorance. It means invisible not just to the eye, but to every detector we have ever built. It means invisible not because we are looking in the wrong direction, but because these things do not appear to interact with light at all, and everything we know how to measure depends ultimately on detecting light in some form. We built the most sensitive machines in the history of our species to find dark matter particles. We buried detectors deep underground to shield them from cosmic radiation, cooled them to within fractions of a degree of absolute zero, filled them with hundreds of tons of the purest xenon ever refined, and waited. We have been waiting. We have found nothing, not a noise, not a whisper, not a single confirmed particle of dark matter has ever been detected by any instrument ever built by human beings. And yet the entire structure of the observable universe, the way galaxies rotate, the way light bends around massive clusters, the way large-scale cosmic structures formed and grew over 14 billion years, all of it requires dark matter to exist. The evidence for its presence is overwhelming. The evidence for what it is completely absent. This is the paradox at the center of modern cosmology. The thing that shapes everything we can see cannot itself be seen. And dark energy is stranger still, because dark energy is not just invisible. Dark energy is doing something to space itself, stretching it apart at an accelerating rate, pushing galaxies away from each other faster than any physical force we understand could account for. And when you try to calculate from first principles what the energy density of empty space should be, using the best theory we have, quantum field theory, you get a number that is 120 orders of magnitude larger than what is observed. That is not a small discrepancy. That is not a rounding error or a measurement problem. That is the worst predictive failure in the history of science, and it sits right at the center of our understanding of the universe. We cannot explain dark energy. We cannot explain dark matter. Together they are 95% of everything. And whatever they are, wherever they come from, they are shaping the fate of every single thing we can see. This is what we are here to do tonight. Not just to catalogue the mystery, though we will do that carefully and in full. We are going to follow the thread from the very beginning, from the first person who noticed that something was wrong, all the way to the present day, where our most sophisticated instruments are beginning to crack the picture open and reveal that the mystery may be even deeper, even stranger than the last century of physics supposed. And along the way, we are going to sit honestly with the possibility that when physics says 95% invisible, it may be pointing at something not just factually surprising, but conceptually revolutionary. A hint that our entire framework for thinking about what exists needs to be rebuilt from the ground up. Part 2. The man at the telescope who should not have been right. The story begins the way most important stories in science begin, with a difficult person noticing something nobody wanted to believe. Fritz Zwicky was a Swiss-born astronomer working at Caltech in the 1930s. He was, by most historical accounts, brilliant and impossible. Colleagues found him abrasive. His confrontational style earned him enemies across the astrophysics community. He called other astronomers spherical bastards, explaining that they were bastards whichever way you looked at them. This is the kind of personality note that historians include, because it explains why, for decades, a scientific discovery that was essentially correct was treated as a curiosity rather than a revolution. In 1933, Zwicky was studying the Coma cluster, The Coma Cluster is a collection of roughly 1,000 galaxies held together by mutual gravity, sitting about 320 million light-years from Earth in the direction of the constellation Coma Berenices. It is one of the nearest and richest galaxy clusters known, a glittering collection of stellar cities clustering together under the pull of their own mass. When Zwicky measured the velocities of the galaxies within the cluster, he found something that should have been impossible. The galaxies were moving far too fast, not slightly too fast, not ambiguously fast, catastrophically, impossibly, unreasonably fast. The velocities he measured were so high that under the influence of only the gravity produced by all the visible matter in the cluster, the galaxies should have been flying apart. The cluster should not have existed. The galaxies should have been scattered across space long ago. And yet there they were, perfectly clustered, orbiting their common center of mass, held together by a gravitational force far more powerful than anything the visible matter could produce. Zwicky calculated that the cluster needed approximately 400 times more mass than could be seen to explain the velocities he was measuring, and he coined a term for whatever was providing that extra gravity: dunkler materie, dark matter. Not dark as in sinister or mysterious in a poetic sense, simply dark as in it does not emit light. He proposed that the Coma Cluster was pervaded by some form of matter that could not be seen, that did not glow, that interacted with visible matter only through gravity. The proposal was radical, it was quantitatively precise, and it was almost completely ignored for the next 40 years. Partly because Zwicky was difficult, partly because the measurement was hard to replicate with the technology of the era, and partly because the idea was so strange that the science community preferred to assume there was some error, some overlooked factor, some more conventional explanation that had not yet been found. There was no conventional explanation, but it took someone else, working decades later with better instruments and a sharper focus, to make the scientific community take the problem seriously. Part 3. The rotation curves that broke the textbook. Vera Rubin was an American astronomer. In the 1970s, working with her colleague W. Kent Ford at the Carnegie Institution of Washington, she was studying the rotation of spiral galaxies. She was asking a straightforward question with a simple prediction attached. How fast do stars orbit the center of their galaxy at different distances from the galactic core? The prediction from Newtonian gravity was clean and well understood. The solar system behaves this way, and we can verify it precisely. Objects closer to the central mass orbit faster. Objects farther away orbit slower. Mercury, the innermost planet, whips around the Sun in just 88 days. Neptune, at 30 astronomical units from the Sun, takes 165 years to complete one orbit. The relationship is mathematically exact. It follows directly from the inverse square law of gravity. As you get farther from the central mass, the gravitational pull weakens and the orbital speed drops. Plotted on a graph with distance from the center on one axis and orbital velocity on the other, you get a rising curve near the center that then falls off smoothly at greater distances. And this is called a Keplerian rotation curve, and it is what every planetary system in the solar system obeys. Rubin and Ford expected to see the same thing in galaxies: star near the center, fast; star far from the center, slow. The curve rises and then falls. The prediction seemed so obvious that they were essentially doing confirmatory work. They expected the galaxies to behave the way physics said they should. The galaxies did not behave the way physics said they should. When Rubin and Ford plotted the rotation curves of spiral galaxies, including our neighbor Andromeda, they found that the curves did not fall off at large radii. The stars at the outer edges of the galaxies were orbiting at roughly the same velocity as the stars near the center, or in some cases even faster. The curves were flat. Disturbingly, persistently, reproducibly flat. Not just for one galaxy, but for galaxy after galaxy after galaxy. Wherever they looked, whatever spiral galaxy they studied, the same anomaly appeared. The outer stars were moving far too fast. If they were orbiting only under the influence of the gravity produced by the visible stars and gas inside the galaxy, they would be moving so fast that they would escape the galaxy entirely. And yet there they were, not escaping, orbiting, happily, stably, locked in their paths despite the fact that nothing in the visible universe was providing enough gravity to explain their velocities. Rubin and Ford concluded that the visible matter in a galaxy, the stars and gas that glow and produce light, was only a small fraction of the total mass. Surrounding every galaxy they studied was an enormous halo of something massive, something that could not be seen, something that extended far beyond the visible disk of stars and provided additional gravity that kept the outer stars from flying away. The mass enclosed within any given galactic radius was far larger than you would calculate from the visible matter alone. The more you looked, the more extra mass you found, and none of it emitted any light. This was the rotation curve problem. And unlike Zwicky's result from the 1930s, Rubin and Ford's measurements were extensive, methodical, consistent, and published over many years in rigorous peer-reviewed papers. By the late 1970s, the scientific community could no longer look away. Something was out there, something massive, invisible, and distributed in a roughly spherical halo around every galaxy anyone could measure. The question was no longer whether dark matter existed. The question was what on earth it was. Part 4. Building the case. Evidence from every direction. What makes dark matter so compelling as a scientific concept is not that we have a single piece of evidence pointing toward it. We have converging evidence from multiple independent directions, each of which forces the same uncomfortable conclusion through a completely different line of reasoning. This convergence is what transformed dark matter from a controversial hypothesis into a central pillar of modern cosmology, even though the fundamental question of what it actually is remains completely unanswered. The first direction is the galaxy rotation curves, which we have just discussed. The second is galaxy cluster dynamics, Zwicky's original observation refined and confirmed through decades of better instruments. But the third direction is perhaps the most beautiful and the most unambiguous, because it involves not measuring motion, but watching light bend. Light does not travel in a straight line through a curved space-time. Massive objects bend space, and the paths photons take through that curved space are deflected in proportion to the mass doing the bending. This is gravitational lensing, a direct prediction of general relativity confirmed since the famous solar eclipse expedition of 1919. When a massive galaxy cluster sits between us and a more distant source of light, the cluster acts as a lens, bending and distorting the light from the background objects into arcs, rings, and multiple images. And here is the crucial point. The amount of bending depends on the total mass of the lens, not the visible mass. The total mass. And when astronomers calculate the mass required to produce the observed lensing distortions, the number they get is consistently 5 to 10 times larger than the mass you can account for from the stars and gas you can see. Whatever is providing that extra gravitational mass is not radiating light. It is not visible. It is dark. And it has to be there because the lensing is real and the lensing has to be produced by something. The fourth direction of evidence involves the cosmic microwave background. When the universe was about 380,000 years old, it cooled enough for protons and electrons to combine into neutral hydrogen atoms. The universe became transparent for the first time, and the photons that had been trapped in the hot plasma streamed freely outward. Those photons are still traveling today, reaching our detectors as a faint glow of microwave radiation filling the sky in every direction, cooled over 14 billion years of expansion to about 2.7 degrees above absolute zero. This is the cosmic microwave background, or CMB, and it is one of the most information-rich signals in cosmology. The The CMB is not perfectly uniform. It has tiny temperature fluctuations of about 1 part in 100,000, corresponding to slight density variations in the early universe. The pattern of those fluctuations, their specific angular scale, their relative amplitudes, the mathematical relationship between their peaks and troughs, is exquisitely sensitive to the composition of the universe. And when cosmologists fit the observed CMB power spectrum to cosmological models, they find that the data only makes sense if the universe contains roughly 5 times more dark matter than ordinary matter, not approximately 5 times. The measurement is precise to about 1%. Dark matter is not a vague addition to the model, it is a precisely measured ingredient of the recipe. The fifth direction is the large-scale structure of the universe. The cosmic web, that extraordinary pattern of filaments, sheets, and voids in which galaxies are arranged like beads on a lace tablecloth, could not have formed the way it did without dark matter. In the early universe, the density fluctuations that eventually grew into galaxies and galaxy clusters started small. They needed something to amplify them, to pull matter together gravitationally into the seeds of structure before the visible matter could do it alone. The timescale problem is severe. Without dark matter providing an additional gravitational scaffolding in the early universe, the visible matter would not have had enough time to clump into galaxies before the universe expanded too fast for gravity to work. Computer simulations of structure formation that include only baryonic matter produce universes that look nothing like the one we observe. Simulations that include dark matter in the right proportions produce universes that match what we see with remarkable fidelity. The cosmic web is the fossil record of dark matter's influence on the early universe. It is structure that could only have been built the way it was built with the help of something we cannot see. Every one of these lines of evidence is independent. Each one involves different observations, different instruments, different physics, and they all point to the same composition. Roughly 5% ordinary matter, roughly 27% dark matter. The convergence is not a coincidence. It is the universe insisting, through 5 different megaphones simultaneously, that most of its matter is of a kind we have never directly detected. Part 5. The smoking gun, the bullet cluster. If you wanted to design an experiment to prove that dark matter exists as a real physical substance and not merely an illusion caused by some modification to the laws of gravity, you could not do much better than what nature provided in the form of the bullet cluster. The bullet cluster is a pair of galaxy clusters that collided several 100 million years ago. It sits about 3.7 billion light-years from Earth in the constellation Carina, and it is called the bullet cluster because the smaller cluster passed through the larger one like a bullet, its gas forming a shock wave that gives it the characteristic elongated shape visible in X-ray observations. Here is why this object is so important. When 2 galaxy clusters collide, the different components of each cluster behave differently. The galaxies themselves, those vast collections of stars, are so sparsely distributed that they pass through each other without collision. Stars in galaxies are separated by such enormous distances relative to their sizes that 2 galaxies passing through each other is mostly empty space passing through empty space, with the galaxies emerging on the far side largely intact. The hot gas that fills the space between the galaxies, the intracluster medium, behaves very differently. This gas is the most massive ordinary matter component of a galaxy cluster, far outweighing all the stars combined, and it is a fluid. When 2 galaxy clusters collide, this gas does not pass through unchanged. It interacts electromagnetically, it drags, it creates shock waves, it slows down. The gas from the 2 clusters ends up concentrated near the collision point, while the galaxies fly through and emerge on either side. This is exactly what the Chandra X-ray Observatory observed when it imaged the bullet cluster. The X-ray emission, which traces the hot gas, is concentrated near the center where the collision happened. Now, if you wanted to know where the mass is, you use gravitational lensing. You map the distortions in the shapes of background galaxies to reconstruct the total mass distribution of the cluster system. And when you do this for the bullet cluster, the mass map does not match the gas distribution. The mass is not concentrated near the center where the gas is. The mass is concentrated around the two galaxy subclusters in the positions where the galaxies went after passing through. The mass followed the galaxies through the collision, not the gas. Something massive, comprising most of the mass of each cluster, passed through the collision without slowing down or interacting electromagnetically, just like the galaxies did, but unlike the gas. This is exactly what dark matter would do. If dark matter is a substance that does not interact electromagnetically, it would pass through the collision undisturbed, just like the galaxies, and the mass map would show mass associated with the galaxy subclusters rather than with the gas. This is what the observation shows. The bullet cluster is, in the words of many cosmologists, the most direct empirical evidence for dark matter yet discovered. Not evidence for some force or modification of gravity. Evidence for an actual substance with mass that does not interact with light. It passed through another cluster and kept going, and the lensing maps show exactly where it went. The observation was published in 2006 by Doug Clow and his colleagues, and it had a significant effect on the scientific debate. Some researchers had been arguing that the rotation curve anomalies and other gravitational discrepancies could be explained not by dark matter but by modified gravity. The idea being that maybe Newton's and Einstein's laws of gravity are slightly wrong at very low accelerations, and that if you fix the law, the extra mass disappears. The bullet cluster makes this much harder to argue. A modification to the laws of gravity would not produce a mass distribution that is physically separated from the baryonic matter. You cannot explain the bullet cluster with modified gravity without introducing something that closely mimics a substance with mass that does not interact with light, at which point you are essentially describing dark matter by another name. The bullet cluster does not prove dark matter beyond all possible doubt. Science does not work that way, but it narrows the alternatives dramatically and it shifts the burden of proof. You do not have to explain why there seems to be extra mass. You have to explain why that extra mass is physically located somewhere different from the visible matter after a collision. That is a much harder problem for any theory that does not involve a non-interacting massive substance. Part 6. What dark matter is not. We have spent considerable effort establishing that dark matter exists and that it is probably a real substance rather than an artifact of misunderstood gravity. Now comes one of the most important and underappreciated parts of the story, which is cataloging all the things dark matter definitely is not. Because a surprising fraction of what physics has learned about dark matter over the past several decades is exclusionary. We know what it cannot be, and what it cannot be turns out to be almost everything we could easily have explained. The first thing dark matter cannot be, and this took a while to establish, is ordinary matter that is simply too faint to see. When the rotation curve problem became widely accepted in the late 1970s, a natural first response was to suggest that the extra mass was just ordinary baryonic matter that happened not to be shining. Dim stars, cold gas, planets, stellar remnants, things made of protons and neutrons, just not luminous ones. This category of candidates was given the charming acronym MACOs for massive compact halo objects. The idea was that the halos of dark matter surrounding galaxies might be filled with black holes, neutron stars, white dwarfs, brown dwarfs, or rogue planets that we simply could not see because they were too cold and too faint. This was a completely reasonable hypothesis, and it was tested with great ingenuity. The method used is microlensing. When a massive compact object passes in front of a distant star, its gravity briefly magnifies the star's light. The brightening is small but detectable and follows a characteristic pattern. Surveys like the MACHO project and EROS monitored millions of stars in the Large Magellanic Cloud, a nearby satellite galaxy, looking for the brief, brightening events that would indicate compact objects in the Milky Way's halo acting as gravitational lenses. They found events, some beautiful and precise ones, but far fewer than the dark matter hypothesis would require. The compact objects detected could account for only a small fraction of the dark matter. The rest had to be something else, and the problem goes deeper than microlensing. The abundance of light elements in the universe, hydrogen, helium, deuterium, and lithium, was set in the first few minutes after the Big Bang in a process called Big Bang nucleosynthesis. The amounts of these elements that were produced depend sensitively on the density of baryonic matter in the early universe. We can measure the abundances precisely, and the result constrains the total amount of baryonic matter in the universe to roughly 5% of the total mass energy content. This is independent of all the galactic dynamics and lensing evidence. Big Bang nucleosynthesis sets a strict ceiling on how much baryonic matter there can be, and that ceiling is 5%. Dark matter is 27%. So dark matter cannot be ordinary matter in any form, whether it is rocks, gas, black holes, or anything else made of protons and neutrons. It has to be something categorically different. The second thing dark matter cannot be is neutrinos. Neutrinos are real, they exist in vast quantities, they interact only weakly with ordinary matter, and they have a tiny but non-zero mass. They sound superficially like dark matter candidates, but neutrinos are produced in such enormous numbers in the early universe, and they move so fast, so close to the speed of light, that they are classified as hot dark matter. And hot dark matter produces a very specific pattern of large-scale structure that does not match what we observe. Hot dark matter would smooth out small-scale density fluctuations and prevent the formation of small structures first, leading to a top-down formation scenario where large structures form before small ones. What we actually observe is bottom-up. Small structures form first and then merge into larger ones. This is what cold dark matter produces. Slow-moving, gravitationally clumping, forming small halos that then aggregate into larger ones. Neutrinos match the wrong pattern. They are ruled out as the primary constituent of dark matter. The third thing, dark matter is not as a black hole of the primordial kind, at least not over a substantial mass range. Primordial black holes formed in the early universe before any stars existed have been proposed as dark matter candidates, and they have their passionate advocates. There was even a brief period of excitement following the LIGO detections of gravitational waves from merging black holes in 2015, when some theorists argued that the black holes detected might be primordial and might constitute dark matter. The argument was simple. We found black holes of about 30 solar masses. That mass range is hard to produce through normal stellar evolution, but fits naturally for black holes formed in the early universe. But subsequent analysis has constrained primordial black holes through multiple independent methods, including the absence of certain microlensing events, the non-distortion of the cosmic microwave background, and the observed gravitational wave background. And in November 2025, the LIGO Virgo and CAGRA collaboration reported a candidate signal from a subsolar mass merger, which would, if confirmed, be strong evidence for a primordial origin for at least some black holes. But even optimistic primordial black hole scenarios cannot account for all of the observed dark matter. Some can exist. Most of the dark matter budget must come from something else. The fourth thing, dark matter is not, and this is the hardest pill for particle physicists to swallow, is any of the particles predicted by supersymmetry that were expected to be found at the Large Hadron Collider. When the LHC was built at CERN and turned on in the first decade of this century, there was cautious optimism in the community that it would find evidence for supersymmetric particles, the lightest of which, called the neutralino, would have been an excellent dark matter candidate. It would be massive, electrically neutral, and interact only through the weak force and gravity. It was the perfect WIMP, a weakly interacting massive particle. The LHC has run for years at its highest energies. No supersymmetric particles have been found, no neutralinos, no evidence of any particle beyond the standard model except the Higgs boson discovered in 2012. The direct detection experiments on the ground have also failed. Xenont, LZ, Pandax 4T. These detectors, filled with hundreds of tons of ultra-pure xenon, cooled to cryogenic temperatures, buried kilometers underground to shield them from cosmic rays, have detected nothing that cannot be explained as background noise from known sources. In fact, these experiments have now reached what physicists call the neutrino floor. They are so sensitive that they are beginning to detect actual solar neutrinos passing through the detector, and those neutrino signals represent the fundamental, irreducible background for any WIMP search. We have pushed the experiment to the absolute limit of what can be done with this technique, and we have found nothing. Dark matter is not ordinary matter. It is not neutrinos. It is probably not primordial black holes alone. It is not the supersymmetric particles that particle physics hope to find. What remains is a list of candidates so exotic that physics has no direct evidence for any of them, and a growing recognition that we may be looking for dark matter in entirely the wrong way. Part 7. The zoo of candidates. What dark matter might be. If we have eliminated the familiar candidates, what remains? The honest answer is that the list of theoretical candidates for dark matter is extraordinarily long, and that different communities of physicists favor different corners of it for different reasons. This is in itself revealing. In a healthy scientific situation, you have one or two strong candidates that most researchers believe in, and you are trying to decide between them. The dark matter situation is different. We have dozens of candidates, each with different mass ranges, different predicted interactions, different detection strategies, and none with decisive observational support. This is the zoo problem. The dark matter zoo contains so many animals that finding one seems almost impossible when you do not know which cage to look in. Let us take a tour. The WIMP, the weakly interacting massive particle, was for decades the leading candidate. A WIMP would have a mass somewhere between 1 and 10,000 times the mass of a proton, and it would interact with ordinary matter through the weak nuclear force, the same force responsible for certain types of radioactive decay. WIMPs have an elegant theoretical motivation beyond just being dark matter. In the early universe, if dark matter was in thermal equilibrium with the hot plasma and then froze out as the universe expanded and cooled, you get approximately the right relic abundance of dark matter today if the interaction cross-section is roughly that of the weak force. This is called the WIMP miracle. The fact that a particle with roughly electroweak scale interactions naturally produces the observed dark matter density seemed to many physicists like it was too much of a coincidence to ignore. Add in the fact that supersymmetry independently predicted a stable particle with almost exactly these properties, and the WIMP became something close to a consensus candidate. That consensus has frayed considerably as direct detection experiments have failed to find anything, and the LHC has found no supersymmetry. WIMPs may still exist. They may simply interact more weakly than expected or have masses outside the current sensitivity range. But the elegant prediction that drove the WIMP paradigm has not paid off. The Axion is a different kind of candidate entirely, and it comes from a completely different theoretical motivation. In the 1970s and early 1980s, Roberto Peccei and Helen Quinn noticed a puzzle in quantum chromodynamics, the theory of the strong nuclear force. The theory seemed to predict a certain kind of charge parity violation in strong interactions that should have been observable, but was not. To solve this problem, they proposed a new symmetry that would naturally suppress the violation. A consequence of this symmetry is the existence of a new particle which Frank Wilczek and Steven Weinberg independently predicted, and which Wilczek named the axion after a laundry detergent, in a moment of levity that tells you something about how seriously theoretical physicists take naming conventions. Axions, if they exist, would be extraordinarily light. We are talking about masses between 10 to the minus 6 and 10 to the minus 3 electron volts, which is billions to trillions of times lighter than an electron. They would be produced in enormous quantities in the early universe and would have velocities far below the speed of light despite their tiny mass because of the specific mechanism by which they are created. This makes them cold, dark matter, consistent with the structure formation observations. Axions interact very weakly with photons, and the search for them involves trying to detect this conversion. In the presence of a strong magnetic field, an axion should occasionally convert into a microwave photon. The ADMX experiment in the United States has been searching for this signal for years, tuning through different frequency ranges corresponding to different possible axion masses. The haystack experiment, the abracadabra experiment, and several European efforts are doing similar work. As of 2025, no confirmed axion signal has been found, though the searches have been exclusionary rather than exhaustive. There are vast regions of the axion parameter space that have never been tested. The searches are accelerating but have years of parameter space left to explore. Sterile neutrinos are a third category. Regular neutrinos are leptons that interact through the weak force and gravity. Sterile neutrinos are hypothetical particles that interact only through gravity, making them even more ghostly than regular neutrinos. They could be produced in the early universe through a mixing mechanism with regular neutrinos. The potential signal for sterile neutrinos is a characteristic X-ray line at a specific energy produced when a sterile neutrino decays. In 2014, a tantalizing 3.5 kilo-electron-volt X-ray line was detected in observations of galaxy clusters by the Chandra and XMM Newton telescopes. For several years, this was discussed as a possible dark matter signal. Subsequent observations with other telescopes have produced conflicting results. Some see the line, others do not. The ESA's XMM Newton mission has continued searching. As of 2025, the situation remains inconclusive. The line may be real and astrophysical in origin. It may be a dark matter signal. The evidence does not clearly distinguish between these possibilities yet. Then there are ultralight axion-like particles, sometimes called fuzzy dark matter. The idea here is that dark matter consists of extremely light bosonic particles with masses around 10 to the minus 22 electron volts, so light that their de Broglie wavelength is enormous on the scale of kiloparsecs. At this mass, quantum effects become relevant at galactic scales. The dark matter would form a quantum condensate, a coherent wave-like state rather than individual particle trajectories. This predicts distinctive patterns in the distribution of matter at small scales, including a suppression of small structures compared to cold, dark matter, which would solve a related puzzle called the missing satellites problem. There are currently too many small, dark matter halos predicted by standard cold dark matter simulations compared to the number of small satellite galaxies we actually observe around large galaxies like the Milky Way. Fuzzy dark matter would naturally produce fewer small halos. The challenge is that very light particles face observational constraints from the Lyman alpha forest, the pattern of absorption of light from distant quasars by intergalactic hydrogen, which requires dark matter to have a sufficiently small de Broglie wavelength. The allowed mass window is narrow but not yet fully closed. Primordial black holes in specific mass windows remain viable. The The sub-solar mass merger candidate detected by LIGO in November 2025 has reinvigorated this possibility. If confirmed, it would be the first direct evidence of sub-solar mass black holes, which can only be primordial and would open the question of how much of the dark matter they could account for. And then there are the candidates we have probably not thought of yet. The history of physics is full of solutions to mysteries that arrived in unexpected forms. The photon was not predicted before Maxwell wrote down his equations of electromagnetism. The Higgs boson was proposed to solve a specific mathematical problem, not to explain an observed phenomenon. It is entirely possible that dark matter is something that no theoretical paper has yet proposed in the right form, waiting to be deduced from a clue we have not yet recognized as a clue. Part 8. The worst measurement in the history of science. We have talked about dark matter. Now we need to talk about the stranger, deeper, more philosophically troubling mystery. The one that comprises 68% of the universe. The one that is not just invisible but is actively doing something to the universe right now. The one that gave Einstein a reason to regret one of his most profound instincts. Dark energy. The story begins in 1917, 2 years after Einstein published the general theory of relativity. He had just written down the field equations that describe how mass and energy curve space-time, and he attempted to apply them to the universe as a whole. And the universe he got from his equations was not the universe he expected. His equations predicted that the universe should be either expanding or contracting. It could not be static. The mutual gravitational attraction of all the matter in the cosmos would cause it to collapse inward, or else the universe was in some state of expansion that countered this. Einstein, like most of his contemporaries, believed the universe was eternal and unchanging. He believed in a static cosmos. And so he introduced a term into his equations, the cosmological constant, lambda, a repulsive energy density of space itself that could counterbalance the gravitational attraction and allow a static universe. He inserted it by hand because the physics seemed to require it, and because the observed universe seemed to be static. 12 years later, Edwin Hubble published his measurements of galaxy velocities. The universe was not static, it was expanding. The very thing Einstein had introduced the cosmological constant to prevent was not only happening, it had been happening the whole time. Einstein reportedly called the introduction of the cosmological constant his greatest blunder and removed it from his equations. The lesson he drew was that the equations had been right and he had flinched. He should have trusted the math. The math said the universe was expanding and the universe was expanding. For most of the rest of the 20th century, cosmologists proceeded on the assumption that the universe was indeed expanding, that the expansion had been set in motion by the Big Bang, and that the combined gravitational pull of all the matter in the universe was gradually slowing it down. Like a ball thrown upward, the universe's expansion was expected to decelerate over time. Whether it would eventually reverse and collapse in a big crunch, or continue expanding forever at decreasing speed depended on the total amount of matter and whether it exceeded a critical density. The key prediction was consistent across all these scenarios. The expansion should be slowing down. In 1998, 2 independent teams of astronomers were racing to measure the deceleration of the universe's expansion using Type Ia supernovae as standard candles. The Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees. Both teams had been collecting data on distant supernova for years. Type Ia supernovae have a characteristic peak brightness that can be calibrated to a standard luminosity, making them reliable distance markers. If you know how bright one should be and you measure how faint it actually appears, you can calculate how far away it is. And if you know the distance and the redshift, you can infer how fast the universe was expanding when that supernova exploded and how the expansion rate has changed since then. This is the tool for measuring the expansion history of the universe. Both teams found the same result, a result so surprising that both initially suspected a systematic error. The distant supernovae were fainter than expected, not by a small amount, fainter by a consistent, significant margin that could not be explained by dust or calibration errors or any known astrophysical effect. The only way to explain the observations was if those distant supernovae were farther away than their redshifts would predict in a decelerating universe. And the only way they could be farther away was if the expansion of the universe had been accelerating, not slowing down, speeding up. The universe was expanding faster today than it was in the past. Something was pushing space apart against the inward pull of gravity. Something was winning the contest against everything that gravity had ever produced. Both teams published their results in 1998. The discovery was met with shock, then excitement, then the gradual dawning recognition that this changed everything. The Nobel Prize in Physics was awarded to Perlmutter, Schmidt, and Rees in 2011 for the discovery. The accelerating expansion of the universe was confirmed by subsequent observations using independent methods, including CMB measurements, baryon acoustic oscillations, and weak gravitational lensing. The acceleration is real. Something is causing it. That something was named dark energy, and the most natural description, the simplest model that fits the data, is that dark energy is the energy density of empty space itself, a cosmological constant. Einstein's blunder was not a blunder. It was the right idea for the wrong reason, introduced to explain a static universe, removed when the universe turned out not to be static, and then required again in an unexpected form to explain why the expansion is accelerating rather than decelerating. The cosmological constant as a modern concept is not entirely Einstein's original idea. It was given a quantum mechanical interpretation by Soviet physicist Yakov Zeldovich in the late 1960s. Quantum field theory says that even in the complete absence of matter and radiation, the vacuum of space is not truly empty. It seethes with quantum fluctuations. Virtual particle-antiparticle pairs blink in and out of existence on timescales too short to violate the uncertainty principle. These fluctuations contribute to the energy density of the vacuum. They give empty space an intrinsic energy, and that energy should, by every calculation quantum field theory knows how to perform, contribute to the cosmological constant. When you calculate what that contribution should be, using the best theoretical framework physics has, you get a number. And then you compare that number to the observed value of the cosmological constant as measured from the supernova data and the CMB. The predicted number and the observed number disagree by a factor of 10 to the power of 120. Let that land for a moment. The prediction is wrong by a factor of 1 followed by 120 zeros. This is not a small error in the theoretical calculation. This is the most catastrophic quantitative disagreement in the history of physics. It is sometimes called the worst prediction ever made by science. The theory predicts something incomprehensibly enormous. What we observe is incomprehensibly tiny, and the ratio between those two numbers is so extreme that it makes the age of the universe in seconds look like a rounding error. There are two possible responses to this catastrophe. Either quantum field theory is deeply wrong about something, or there is some extraordinarily precise cancellation that removes most of the vacuum energy and leaves only a tiny residual. If there is a cancellation, it has to be precise to 120 decimal places. No physical mechanism for such a cancellation has ever been identified. The cosmological constant problem is the deepest open wound in theoretical physics, and it sits at the center of the most abundant substance in the universe. Part 9. Dark energy is changing, and that changes everything. For about 25 years after the discovery of the accelerating expansion, the simplest model held. the cosmological constant fits the data, lambda, a fixed, unchanging energy density of empty space, the same at every point in space and at every moment in time. Dark energy in this model is not dynamic. It does not evolve, it does not change. It is simply the energy of the vacuum, constant since the Big Bang, constant until the heat death of the universe. The lambda CDM model, lambda for the cosmological constant and CDM for cold dark matter, became the standard model of cosmology, and it passed test after test for 2 decades. Every observation was consistent with it. The universe's expansion history fit the prediction. The CMB power spectrum fit the prediction. The distribution of large-scale structure fit the prediction. Lambda CDM was not a perfect theory, but it was a remarkably accurate one. And then, in 2024, the first results from the Dark Energy Spectroscopic Instrument, DESI, began to complicate the picture. DESI is an instrument at the Kitt Peak National Observatory in Arizona that measures the spectra of galaxies using 5,000 robotic fiber positioners to simultaneously observe 5,000 objects in the sky every time it takes a pointing. It has been systematically mapping the 3-dimensional distribution of galaxies across vast swathes of the universe, creating the most precise measurement of baryon acoustic oscillations ever assembled. Baryon acoustic oscillations are a particular pattern in the distribution of galaxies that serves as a standard ruler. Sound waves propagating through the hot plasma of the early universe froze into the distribution of matter when the universe cooled and became transparent. These frozen patterns appear as a characteristic scale in the galaxy distribution, and by measuring that scale at different cosmic epochs, you can track how the expansion rate has changed over time. When DESI's first year of results was published in 2024, the data was consistent with the standard model, but when combined with other datasets including supernova measurements and CMB data, the combined evidence showed hints of a departure from a simple cosmological constant. The dark energy equation of state, the parameter that quantifies the relationship between dark energy's pressure and density, appeared to be changing over time. A pure cosmological constant has an equation of state exactly equal to -1. If dark energy was simply the energy of the vacuum, this parameter would be constant and exactly -1. The combined data set suggested the parameter was evolving, was perhaps not exactly -1 in the past. The March 2025 results from DESI's second data release strengthened these hints considerably. The full 5-year DESI survey results, analyzing a map built from over 47 million galaxies and quasars, combined with cosmic microwave background data from Planck and the Atacama Cosmology Telescope and multiple supernova datasets, showed evidence for evolving dark energy at a statistical significance of between 3.5 and 3.9 sigma, depending on which supernova dataset was included. This is below the 5 sigma threshold physicists typically require for a discovery, but it is significant enough to be taken seriously. The leading DESI scientists were direct. "We are guided by Occam's razor," said Will Percival, co-spokesperson for DESI and professor at the University of Waterloo. "The simplest explanation for what we see is shifting. It is looking more and more like we may need to modify our standard model of cosmology, and evolving dark energy seems promising. If dark energy is indeed changing over time, the cosmological constant is ruled out. You need something more, something dynamic, a field, an energy component that evolves as the universe expands and whose equation of state changes as that evolution proceeds. The simplest such candidate is called quintessence, a name borrowed from ancient Greek cosmology's concept of the fifth element, the ethereal substance of the celestial spheres, updated for modern field theory into a slowly rolling scalar field that fills all of space and whose energy density changes over cosmic time like a ball rolling down a very shallow hill. Quintessence predicts that dark energy's equation of state changes over time, becoming less negative as the universe ages, which is broadly consistent with what DESI is seeing. But if quintessence is right, it raises its own profound questions. What is this scalar field? Where did it come from? Why is it rolling at just the right rate to produce the observed acceleration? And what does it do to the far future of the universe? One remarkable implication of the DESI results worked out by a Cornell physicist using the new data is that if dark energy is weakening over time, then rather than expanding forever, the universe might eventually stop expanding and reverse into a contraction, ending not in a cold, dark heat death, but in a big crunch. The calculation suggests the universe may reach maximum size in about 11 billion years before collapsing back in on itself, compressing everything into a final singularity about 20 billion years from now. The universe on this picture has a lifespan of about 33 billion years, and we are roughly at the halfway point. These are preliminary results. The statistical significance is not yet at discovery threshold. Alternative explanations have not been ruled out. Systematic errors in the supernova data sets remain possible sources of confusion, and astronomers disagree vigorously about which supernova compilation is most reliable, but the direction of the evidence is consistent and getting stronger. Dark energy may not be constant, and if it is not constant, physics has a great deal of explaining to do. Part 10, the Hubble tension, a universe that cannot agree with itself. There is another problem sitting in the middle of cosmology that has been growing more insistent for the past decade and shows no sign of resolving. It is called the Hubble tension, and it is, at its core, a disagreement between two different ways of measuring the most fundamental number in cosmology. The Hubble constant, h0, describes how fast the universe is currently expanding. It tells you how quickly galaxies at any given distance are receding from us due to the expansion of space. The higher the Hubble constant, the faster the expansion. This single number is one of the most important parameters in all of cosmology, and the universe cannot seem to give us a consistent answer for it. There are two main ways to measure the Hubble constant. The first uses the early universe as a starting point. You study the cosmic microwave background, use the fluctuation pattern to extract the cosmological parameters, run the expansion forward 14 billion years under the lambda CDM model, and predict what the Hubble constant should be today. The Planck satellite's analysis of the CMB gives a value of approximately 67 kilometers per second per megaparsec. The second method uses the local universe directly. You build a so-called cosmic distance ladder using Cepheid variable stars whose pulsation period tells you their luminosity to calibrate distances to nearby galaxies, then using the calibrated distances to those galaxies to calibrate type Ia supernovae, and then measuring the recession velocities of distant galaxies at various distances to extract h0 directly from the data. The H0ES collaboration, led by Adam Rees, has made these measurements with increasing precision over many years using data from the Hubble Space Telescope and more recently the James Webb Space Telescope. Their value is approximately 73 kilometers per second per megaparsec, 67 versus 73, a difference of 9%. And this disagreement is not a matter of imprecision. Both measurements have uncertainties of only about 1%. The discrepancy is statistically significant, sitting at about 5 sigma, which is the threshold normally used in physics to declare a discovery. The two measurements of the same physical quantity, using completely independent methods, are irreconcilably different. The early universe says the expansion should be happening at 1 speed. The local universe says it is happening 9% faster. Something is wrong. Either one or both of the measurements has an unidentified systematic error, or the standard model of cosmology is missing something fundamental that changes the expansion history between the early and late universe. Astronomers have searched exhaustively for systematic errors in both measurements. The Cepheid calibration has been checked and rechecked, with the James Webb Space Telescope, which has sharper resolution and can better distinguish individual Cepheid stars from background contamination. The JWST data has not resolved the tension. It has, if anything, confirmed the higher local value. The CMB analysis has been scrutinized with data from the Atacama Cosmology Telescope and other ground-based experiments. The lower early universe value remains robust. The tension is not going away, it is sharpening. The most exciting possibility is that the Hubble tension is telling us about real new physics. If dark energy was stronger in the early universe than it is now, if there was an early dark energy component that has since faded, it could change the pre-recombination expansion rate and shift the CMB prediction toward higher values. Several proposals for early dark energy have been made and tested. They help, but they do not fully resolve the tension while remaining consistent with all other observations. Alternative models involving modified gravity, interacting dark matter and dark energy, or extra radiation in the early universe have also been proposed. None is fully satisfactory. The Hubble tension matters for our story because it suggests that whatever dark energy is, it may not have been the same throughout cosmic history. The universe expanded at a rate in its early phases that does not seamlessly connect to the rate we measure locally today. Something interrupted or modified the expansion history, and whatever did it has not yet been identified. The dark universe, 95% of everything, may have a more complex dynamical history than any of our current models capture. Part 11, the missing baryons and the cosmic web. Here is a twist that does not get discussed enough, and it complicates the story in an interesting direction. Dark matter and dark energy are not the only invisible things in the universe. Even within the visible 5%, there is a significant fraction of ordinary baryonic matter that has been hiding from us for decades. In the early universe, shortly after the Big Bang, the amount of baryonic matter can be precisely calculated from Big Bang nucleosynthesis and from the CMB fluctuation pattern. The total baryonic budget is well constrained, but when astronomers take inventory of all the ordinary matter they can see in the relatively nearby recent universe, in stars, in galaxies, in the gas within galaxies, and in the hot gas in galaxy clusters, the sum does not add up. Roughly half of all the baryonic matter in the universe in the last few billion years has been missing. Not in the exotic dark matter sense, just missing. Not where the theory says it should be. This is called the missing baryons problem, and its solution is one of the quieter successes of recent observational astronomy. The missing baryons are probably in what is called the warm-hot intergalactic medium, abbreviated WIM. This is a diffuse, low-density plasma occupying the filaments of the cosmic web, the vast network of thread-like structures connecting galaxies and galaxy clusters across the universe. The WIM has temperatures between 100,000 and 10 million Kelvin, which makes it extremely difficult to detect. It is too cool to emit strongly in X-rays and too hot to emit strongly in ultraviolet light. It sits in a gap between conventional astronomical wavelengths. It can be detected through specific ultraviolet and soft X-ray absorption lines when its gas absorbs light from background quasars, but the signal is faint and the observations are challenging. In 2020, a paper in Nature reported a detection of the missing baryons through a technique called the kinetic Sunyaev-Zeldovich effect, in which the microwave background photons are scattered by the moving electrons in the WIM, leaving characteristic patterns. Multiple subsequent observations have strengthened the case that most of the missing baryons are indeed in these diffuse filaments. The universe's ordinary matter is distributed not just in the bright galaxies we can easily see, but in a vast, faint web of gas connecting them, following the gravitational scaffolding of the dark matter halo network. This matters conceptually because it reminds us that even within the visible universe, within our 5%, invisibility comes in degrees. The universe is less transparent than we supposed, even at the level of ordinary matter. The filaments of the cosmic web were invisible not because they do not interact with light, but because the light they produce or modify is just barely too faint to detect with older instruments. The James Webb Space Telescope and next-generation radio observatories are beginning to map these structures in new ways. But the point stands, even within the familiar 5%, a significant fraction was effectively hidden until recently. Part 12. The alternatives? What if gravity is wrong? Before we go any further into the candidate particles and detection experiments, we owe an honest discussion to the alternative hypothesis. The one that says the problem is not that we are missing a substance, but that we have the wrong theory of gravity. Modified Newtonian dynamics, called MOND, was proposed by Israeli physicist Mordechai Milgram in 1983. His observation was elegant and specific. The anomalous galactic rotation curves do not appear at a particular radius in galaxies. They appear when the gravitational acceleration falls below a specific critical value, roughly 1.2 times 10 to the minus 10 meters per second squared. This value is extraordinarily specific, and Milgram proposed that it represents a threshold below which the law of gravity changes. When accelerations are above this value, Newtonian gravity operates normally. Below it, gravity falls off more slowly than the inverse square law predicts, and this modified behavior is what produces the flat rotation curves without any dark matter. MOND is remarkable in its predictive power for individual galaxies. Given only the distribution of visible matter in a galaxy, MOND can predict the rotation curve with striking accuracy across many different galaxies, spanning a wide range of sizes and types. This is something that dark matter does not obviously do. In dark matter models, the rotation curve depends on the distribution of dark matter in the halo, which has to be fit to the observations and is not directly predicted from the visible matter distribution alone. MOND, by contrast, derives the rotation curve purely from the visible matter with one free parameter, the critical acceleration, which appears to be universal across many galaxies. This success is not trivial and it demands explanation. The problem is that MOND does not work everywhere. Galaxy clusters require significantly more mass than MOND can provide, even with its modified gravity. The bullet cluster is a serious challenge because the separated mass distribution suggests a substance that physically moved which modified gravity cannot explain. The cosmic microwave background anisotropies require dark matter to explain their pattern. Large-scale structure formation requires the gravitational scaffolding of dark matter. When MOND is applied to these problems, it fails quantitatively. It can be extended into relativistic frameworks by various researchers, but in every case, the extension ends up requiring something that looks very much like dark matter in most contexts. The consensus in cosmology is that MOND captures something real about the relationship between visible matter and dynamics in galaxies, but is not the full answer. A more recent and more mathematically sophisticated alternative is Eric Verlinder's emergent gravity proposal published in 2016. Verlinder, a Dutch physicist at the University of Amsterdam, argues that gravity is not a fundamental force, but an emergent thermodynamic effect similar to how temperature and pressure emerge from the collective behavior of many particles. In his framework, the universe is filled with a medium of quantum information associated with dark energy, and the interaction between this information and ordinary matter produces an additional gravitational effect that mimics dark matter in galaxies. The proposal is mathematically interesting and has made some specific predictions about the distribution of gravitational anomalies in galaxies that can be tested observationally. Results have been mixed. Some observational comparisons favor Verlinder's predictions in certain galaxy types. Others do not match. The proposal has not been extended to a fully consistent relativistic theory and has not been shown to handle galaxy clusters, CMB, and large-scale structure simultaneously. What both MOND and emergent gravity tell us is that the pattern of mass and dynamics in galaxies is remarkably regular. The relationship between the distribution of visible matter and the observed dynamics is tight enough and universal enough to suggest that whatever dark matter is, or whatever modification of gravity is responsible, it is intimately connected to the distribution of ordinary matter in a way that the simplest dark matter models do not obviously explain. This is called the baryonic Tully-Fisher relation in spiral galaxies and the RAR, radial acceleration relation, in a broader context. It says that the centripetal acceleration you measure in galaxies is a precise function of the gravitational acceleration due to visible baryonic matter alone. Not a rough correlation, a tight, nearly scatter-free relation across galaxies of vastly different sizes, luminosities, and morphologies. Dark matter models can reproduce this relation if you assume specific statistical relationships between the dark matter, halo properties, and the baryonic content. This is called galaxy halo connection modeling, and it requires some fine-tuning. Whether that fine-tuning is natural, whether it can be derived from fundamental physics, or whether it implies something deeper about the relationship between dark and ordinary matter, is actively debated. The radial acceleration relation may be the most important observational clue we have about the nature of dark matter, and we do not yet know how to read it. Part 13. The machines built to answer the question. The failure of direct detection experiments to find WIMPs has been one of the most consequential non-discoveries in the history of physics. Not because failure is surprising in science, but because the failure is so comprehensive and so systematic. We did not just fail to find dark matter particles with one experiment. We built increasingly sensitive generations of experiments, each several times more capable than its predecessor, pushed the sensitivity across many orders of magnitude of interaction cross-section, reached the fundamental background limit imposed by solar neutrinos, and found nothing. The LEX Zeppelin experiment, LZ, is the successor to the LEX detector that operated in the Black Hills of South Dakota at the Sanford Underground Research Facility. LZ uses 10 tons of liquid xenon cooled to -103 degrees Celsius in a detector installed 1,500 meters underground. The outer xenon tank acts as an active veto for background radiation. The inner region of xenon is the active target. When a dark matter particle would scatter off a xenon nucleus, it would produce both photons from scintillation and electrons from ionization. The ratio of the two signals distinguishes nuclear recoils from electronic recoils and allows discrimination between signal and background. LZ published results in 2023 and 2024 that set the world's most stringent limits on the interaction cross-section of WIMPs with nucleons across a wide range of WIMP masses. It found no dark matter signal. The Xenont experiment at the Gran Sasso National Laboratory under the Apennine Mountains in Italy published results in 2023 that included the first detection of solar neutrinos through coherent elastic neutrino nucleus scattering, demonstrating that the experiment had indeed reached the neutrino floor. This is simultaneously a remarkable physics achievement and a sobering milestone for dark matter searches. The solar neutrino background cannot be removed by better shielding or better veto systems. It is an irreducible physics background. To push sensitivity beyond the neutrino floor, a new generation of detectors would need to use directional information, measuring not just the energy of a nuclear recoil, but the direction from which the recoil came. Dark matter particles streaming through from the direction of our galactic motion through the dark matter halo would produce a characteristic directional signature that solar neutrinos would not. But directional detectors are technologically far more challenging, require different materials, and cannot yet reach the sensitivity of xenon detectors. The next generation of experiments is being designed with this challenge in mind. Panda X4T operating at the China Jinping Underground Laboratory, is the third of the 3 massive liquid xenon experiments that have been competing and collaborating in the WIMP search. Its results are consistent with the others. No signal, tight limits. The story is the same in every laboratory. There are also searches at particle colliders, most prominently the ATLAS and CMS experiments at the Large Hadron Collider. Dark matter particles, if they can be produced in proton-proton collisions, would escape the detector without being directly detected, carrying away energy and momentum that would appear as a measurable imbalance in the collision products. This is called the missing transverse energy signature, and it has been searched for extensively. In 2025, ATLAS released results on so-called emerging jets, a signature where dark matter is produced alongside visible matter in complex particle showers that emerge mid-flight through the detector, setting the first exclusion limits on dark hadrons in this new channel. No dark matter signal has been found at the LHC in any search channel. What remains? The Axion searches are making progress. ADMX has been tuning through the mass range of about 1 to 10 microelectron volts, which is where the most theoretically motivated axion masses sit for standard QCD axions. The search is painstaking. Each frequency corresponds to a specific mass, and the expected signal is so faint that integration times of days per frequency range are required. Haystack uses a quantum squeezing technique to beat the standard quantum limit on noise, dramatically improving sensitivity. These experiments have excluded portions of the theoretically favored parameter space, but large regions remain to be explored. The Rubin Observatory completed at the Vera C. Rubin Observatory in Chile began its legacy survey of space and time in 2025. Over 10 years, it will image the southern sky every few nights in multiple wavelengths, creating the deepest, widest, most time-resolved map of the sky ever produced. It will detect billions of new galaxies, measure weak gravitational lensing at unprecedented statistical power, discover many thousands of new, strong lensing systems, and constrain the distribution of dark matter in halos around galaxies and galaxy clusters with extraordinary precision. It will not tell us what dark matter is, but it will tell us with great precision where it is and how it is distributed, which constrains the theoretical candidates significantly. The Square Kilometre Array, SKA, is a radio telescope array being built in South Africa and Australia, which when complete will have a collecting area of a square kilometre, making it the largest radio telescope ever constructed. Among its scientific goals is a census of hydrogen across the universe using the 21 centimetre line, the hyperfine transition we discussed at the very beginning of this journey. By mapping neutral hydrogen distribution at cosmic scales and through cosmic time, it will probe the matter-power spectrum and dark matter clustering with extraordinary precision. It will also search for 21 centimetre signals from the epoch of rayonization, the period when the first stars and galaxies lit up the universe and ionized the neutral hydrogen. This epoch is a sensitive probe of dark matter properties because the way small structures form in the early universe depends on the dark matter particle mass and interaction history. The Euclid satellite, launched by the European Space Agency in 2023, has been mapping the geometry of the universe using weak gravitational lensing of billions of galaxies. Its goal is to measure the dark matter distribution and the growth of structure across cosmic time with enough precision to constrain dark energy models and test modifications of gravity. First science results began appearing in 2024, and more comprehensive results are expected through 2026 and beyond. Euclid cannot directly detect dark matter particles, but by mapping how dark matter has clustered over billions of years, it can tell us whether dark matter behaved exactly as cold dark matter models predict, or whether there are departures at small or large scales that hint at different particle physics. These experiments represent a coordinated global effort spanning underground laboratories, space telescopes, and radio arrays on multiple continents. The investment is enormous. The question being asked is among the most important ever posed in science. And the answers are coming slowly through exclusion and constraint, through tightening the space of possibilities rather than finding a signal. It is hard science of the most demanding kind. Part 14. The Gamma Ray Clue. In November 2025, something happened that sent a ripple of excitement through the astrophysics community. A paper published by researchers from the University of Tokyo reported a high-energy gamma-ray signal detected from the center of a nearby galaxy that fits the expected footprint of dark matter particles annihilating with each other. Dark matter particles that interact through the weak force, if they are their own antiparticles, as many WIMP models predict, could annihilate in pairs to produce gamma rays. The galactic center, where dark matter density is expected to be highest due to gravitational concentration over billions of years, is the most natural place to search for this signal. And a signal consistent with that expected from dark matter annihilation had been detected. The community greeted this with the appropriate mixture of excitement and caution. The galactic center is the most complex astrophysical environment in the galaxy. It is crowded with pulsars, molecular gas, X-ray binaries, stellar winds, and active regions of star formation, all of which can produce gamma rays through processes that have nothing to do with dark matter. Disentangling a putative dark matter signal from these astrophysical backgrounds is extraordinarily difficult. Similar claims have been made before. In 2014, a gamma-ray excess was detected from the galactic center by the Fermi Gamma-Ray Space Telescope that some researchers attributed to dark matter annihilation, producing widespread excitement. Subsequent analysis has provided evidence that much of the excess can be accounted for by a population of unresolved millisecond pulsars that are simply too numerous and too faint for Fermi to resolve individually. The debate about the galactic center excess has continued for a decade without resolution. The 2025 signal is different in some respects. It involves higher energy gamma rays, a different spectral signature, and a different source galaxy. The Cherenkov telescope array currently under construction will be sensitive to the relevant energy range with much better angular resolution and energy resolution than previous instruments. Whether this signal represents the first genuine dark matter detection or another astrophysical mimic remains to be determined, but it illustrates the pattern of dark matter science. Hints appear. Systematic analysis follows. Alternative explanations are explored. The verdict takes years. Part 15. What the Milky Way tells us. The dark matter halo surrounding our own galaxy is the nearest laboratory we have for studying this invisible substance. And our own galaxy has been telling us things about dark matter for decades, some of which fit the standard model and some of which don't. The standard cold dark matter model makes specific predictions about the density profile of dark matter halos. The Navarro-Frank-White profile, named for the physicists who derived it from N-body simulations in the 1990s, predicts that dark matter density rises steeply toward the center of halos, following what is called a cuspy profile. The density diverges toward a singularity at the center of the halo. Observations of nearby dwarf galaxies, which should be dominated by dark matter with minimal contamination from the complex baryon physics that complicates analysis in large galaxies, have instead found density profiles that are flatter at the center, what are called core profiles. This discrepancy between simulated cusps and observed cores is called the cusp-core problem. Similarly, cold dark matter simulations predict that large galaxies like the Milky Way should be surrounded by hundreds to thousands of small satellite galaxies, tiny dark matter halos large enough to have formed stars. We observe far fewer. The Milky Way has roughly 60 known satellites, and surveys suggest perhaps a few hundred total in the observable region. This is the missing satellites problem. Cold dark matter simulations also predict that the most massive satellite halos should have very high central densities, high enough that the stars within them would be orbiting too fast to match the observed stellar velocities in the Milky Way's dwarf spheroidal satellite galaxies. They do not. This is the too big to fail problem, named for the observation that the dark matter halos predicted to be too massive to avoid forming stars are absent from the observed satellite population. These three problems, cusp core, missing satellites, and too big to fail, have dominated theoretical dark matter physics for decades. They could all be resolved by energetic feedback processes in the baryonic physics, the injections of energy from supernova explosions and radiation pressure from young stars that can heat and redistribute gas in the centers of dwarf galaxies, expelling it, and in the process, reducing the central dark matter density. Hydrodynamic simulations that include these processes can produce chord profiles and fewer, more diffuse satellites. But the required feedback is energetically demanding, and the question of whether it operates at the required scale is debated. Alternatively, the problems might indicate that dark matter is not entirely cold. If dark matter has some small velocity dispersion, if it is warm rather than cold, it would smooth out small-scale density fluctuations, suppress the formation of the smallest halos, and produce less cuspy density profiles. Warm dark matter with particle masses around a few kilo-electron-volts, corresponding to candidates like sterile neutrinos, has been proposed as a resolution. But it must be warm enough to solve the small-scale problems without being so warm that it destroys large-scale structure, which requires fine-tuning. The fuzzy dark matter candidate we discussed earlier, ultralight axion-like particles with masses around 10 to the minus 22 electron volts, provides another resolution. At these particle masses, quantum effects produce a wave-like dark matter with a natural minimum length scale called the de Broglie wavelength. This naturally suppresses structure below that scale and produces chord density profiles in small halos. The challenge is that strong lensing constraints and Lyman alpha forest measurements require the de Broglie wavelength to be shorter than fuzzy dark matter in the original mass range would predict. The allowed window is narrow, but may still exist. The Milky Way is a puzzle within the larger puzzle. Our own galaxy is simultaneously our best laboratory and our most complicated one because we are inside it, embedded in its disk of stars, and cannot see its large-scale structure as clearly as we can see more distant galaxies from outside. The Gaia satellite, which has measured precise positions and velocities for over 1 billion stars in the Milky Way, is providing unprecedentedly detailed maps of stellar motions that can be used to infer the gravitational potential of the galaxy and from that, the distribution of dark matter. The results have generally confirmed that dark matter exists in a roughly spherical halo, but details of the density profile, the shape of the halo, and the presence of substructure are still being extracted from the data. Part 16. The identity crisis. What are we asking? At some point in studying this problem, you have to step back and ask whether we are asking the right questions. Whether the framework we are using to think about dark matter and dark energy is adequate to the problem. Whether physics is in a position where it can identify the solution, even if the solution is out there. There is a version of this story where dark matter and dark energy are specific particles and fields that physics will identify in the coming decades, whose properties fit naturally into an extended standard model or a theory of quantum gravity, and whose detection will close the mystery in a satisfying way that makes the whole history of the search feel like a necessary journey toward an answer that was always there. This is the optimistic version. There is another version where the 95% of the universe we cannot see is a signal that our entire conceptual framework is incomplete, in a more radical way. Not just missing a particle or two, but missing something about the nature of what exists, about the relationship between gravity and quantum mechanics, about what space and time are at the most fundamental level. In this version, dark matter and dark energy are the symptoms, and the disease is a gap in our physics so deep that we cannot yet see its edges. Consider what we know about quantum gravity. We have two frameworks, general relativity and quantum mechanics, each extraordinarily successful in its domain, each completely incompatible with the other when pushed to extremes. At the scales where dark matter and dark energy matter most, cosmic scales, galactic scales, the universe as a whole, we use general relativity, and we layer dark matter and dark energy on top of it as additional ingredients needed to make the equations balance. But we have no quantum theory of gravity. We do not understand what space-time is at the Planck scale. We do not understand what the vacuum is at the quantum level, which is directly connected to the cosmological constant. It is at least possible that the resolution to both dark matter and dark energy will require a new framework for gravity that simultaneously explains what dark matter particles are and why the vacuum has the energy it has. Some theoretical ideas in this direction do exist. In loop quantum gravity, space-time has a discrete structure at the Planck scale, and the effective gravitational behavior at large scales may differ from classical general relativity in ways that could mimic dark matter or dark energy effects. In certain theories of extra dimensions, the gravity we observe is only a slice of a higher dimensional gravitational interaction, and the additional dimensions could produce effects that mimic dark matter in the four-dimensional world we inhabit. In string theory, a vast landscape of possible vacuum states allows for a selection of the cosmological constant value through anthropic reasoning, though this is philosophically controversial and not testable in any conventional sense. The point is not that any of these specific ideas are correct. The point is that the 95% problem may be telling us something about the foundations of physics that we are not in a position to hear yet because we are not asking the question in the right language. The history of science has precedents. Newtonian mechanics was extraordinarily successful within its domain and broke at speeds approaching light and at quantum scales. Its breakdown was not a simple matter of adding corrections. It required entirely new conceptual frameworks, special relativity and quantum mechanics that reframed what space, time, and matter fundamentally are. The dark matter and dark energy problems may be pointing at a similar kind of conceptual revolution, one we cannot yet see coming because we are embedded in the current framework. Part 17. How it fits together, the cosmic web and dark matter. One of the most beautiful and underappreciated aspects of this whole story is the way dark matter and the structure of the observable universe are inseparably linked. Not just in the abstract sense that dark matter provides gravitational scaffolding. In the very specific, very visible, very observationally precise sense that the large-scale structure of the universe, the cosmic web that extends across hundreds of millions of light-years, is the direct imprint of dark matter's behavior in the early universe. The Millennium Simulation, and its successors like the illustrious TNG and Eagle simulations, are some of the most computationally ambitious projects in the history of science. They simulate the evolution of the universe from the smooth, nearly uniform conditions of the early universe through 14 billion years of gravitational collapse, gas cooling, star formation, feedback from supernovae and active galactic nuclei, and dark matter structure formation, producing synthetic universes that can be compared directly with observations. When you run these simulations with the right amounts of dark matter and dark energy, the synthetic universe they produce is remarkably like the one we observe. The distribution of galaxies, the statistics of galaxy clusters, the abundance of voids, the pattern of filaments in the cosmic web, the galaxy rotation curves, the gravitational lensing statistics, All of it emerges naturally from the fundamental initial conditions and the physics of cold dark matter interacting gravitationally, while ordinary matter forms stars and galaxies within the dark matter halos. This is a striking success. We do not know what dark matter is, but we can simulate its gravitational effects to produce a universe that matches what we observe across many orders of magnitude in scale and many different types of observations. This is why cosmologists are confident that dark matter exists, that it comprises roughly 27% of the cosmic energy budget, that it is cold, and that it is gravitationally self-consistent. The concordance is not the result of fitting one or two data points. It is the result of matching a complex, multi-dimensional observational dataset with a model that has a small number of free parameters. The fact that it works is not trivial. The cosmic web itself is the fossil record of dark matter evolution. The filaments trace the paths along which dark matter flowed under gravity over billions of years. The nodes where filaments intersect are the most massive concentrations, the galaxy clusters. The voids are the regions depleted of both dark matter and ordinary matter. Galaxies are the candles that light up the underlying dark matter scaffolding, but the scaffolding was there first and is more massive by far. The universe you see in a deep image from the Hubble or James Webb Space Telescope, those thousands of galaxies scattered across the field, each containing hundreds of billions of stars, is a map drawn by dark matter. The dark matter drew the lines, the ordinary matter filled them in with light, and within each of those galaxies the dark matter halo extends far beyond the visible disk. The Milky Way's dark matter halo probably extends to distances of hundreds of thousands of light years, far beyond the outermost stars of the galactic disk. When you look at another galaxy and see a spiral disk of stars 100,000 light years across, you are seeing only the luminous tip of a much larger invisible structure that dwarfs the visible portion. The galaxy you can see is embedded in a sphere of dark matter that you cannot see, and that sphere is where most of the mass is. The stars are the decoration on a dark matter halo. The halo is the galaxy. Part 18. Watching the invisible collide. Gravitational lensing as dark matter cartography. If dark matter cannot be seen directly, the next best thing is to see what it does to the light around it. Gravitational lensing has become the most powerful tool for mapping dark matter at cosmic scales, and recent years have brought an explosion of lensing measurements that are beginning to produce detailed maps of the dark matter universe. Weak gravitational lensing is the subtle distortion of the shapes of background galaxies by the gravitational fields of foreground matter. Each individual galaxy is distorted by a tiny amount, and the signal cannot be measured for any single galaxy because galaxies have intrinsic shapes that vary. But by averaging over many thousands of galaxies in a statistical sense, the correlated distortions produced by foreground dark matter structure become measurable. It is like trying to detect a gentle breeze by watching individual leaves. No single leaf tells you much, but thousands of leaves, all blowing in the same direction, give a clear signal. The DES, or Dark Energy Survey, used a 4-meter telescope in Chile to image 350 million galaxies and measure their shapes with sufficient precision to construct maps of dark matter projected along the line of sight across much of the southern sky. The resulting maps show the cosmic web of dark matter in striking detail, revealing filaments, clusters, and voids across billions of light years. These measurements also provided stringent constraints on a combination of parameters called sigma 8 times omega matter to the 0.5, which characterizes the amplitude of matter clustering. And this parameter has its own tension. The value inferred from weak lensing in the late universe is somewhat lower than the value predicted by the CMB combined with the standard lambda CDM model. Not as dramatic as the Hubble tension, but present and persistent. Something may be different about how dark matter clusters on small scales compared to what simple cold dark matter models predict. The Decade Survey, published in December 2025, extended the DES analysis to a new region of the sky using the DCAM instrument, measuring shapes for 107 million additional galaxies across 5,400 square degrees. This doubled the available galaxy shapes for cosmological inference outside the original DES footprint and provided an independent test of the lambda CDM model. The results are broadly consistent with the standard model but add precision to the hints of tension in matter clustering amplitude. Strong gravitational lensing, where the lens is massive enough to produce multiple images, arcs or Einstein rings of background sources, provides a completely different and complementary probe. Strong lensing systems act as natural telescopes, magnifying background sources by factors of 10 to 100. They also encode detailed information about the dark matter distribution within the lensing galaxy or cluster, including the presence of dark matter substructure. The number and properties of bright knots within Einstein rings depend on the population of dark matter subhalos within the lens. Recent analyses using machine learning techniques to identify and model strong lensing systems in Hubble and JWST images have found evidence for dark matter substructure consistent with cold dark matter predictions, though the statistics are still limited. As Euclid and Rubin discover and resolve hundreds of thousands of strong lensing systems over the coming years, this will become a powerful probe of dark matter particle properties. Part 19, the neutrino revolution and its lessons. When we think about why dark matter detection has been so frustrating, it is useful to remember that physics has successfully detected another nearly invisible particle, one that interacts even more weakly with ordinary matter than WIMPs are expected to, and one whose existence was also predicted theoretically long before it was detected experimentally. The neutrino provides a lesson in what is required to detect something that barely interacts with the world. Wolfgang Pauli proposed the neutrino in 1930 to explain why the energy spectrum of electrons emitted in beta decay was continuous rather than discrete. If a neutron decayed only into a proton and an electron, energy and momentum conservation would require the electron to be emitted with a specific energy. But electrons were observed with a range of energies. Pauli suggested a third particle was being produced, one that carried away the missing energy. He famously apologized for predicting a particle that could never be detected because it interacted so weakly that passing through the Earth was almost nothing to it. It took 26 years, but in 1956, Clyde Cowan and Frederick Reynes detected neutrinos directly using a nuclear reactor in South Carolina that produced enormous fluxes. They detected the antineutrinos through inverse beta decay, a process in which an antineutrino strikes a proton and produces a neutron and a positron, with the positron annihilating against an electron to produce a coincident gamma-ray signal. The experiment required enormous fluxes of antineutrinos and an ingenious detector design, but it worked. Pauli received the news in a telegram while attending a physics conference and replied with characteristic directness. The lesson for dark matter is that a particle can be extraordinarily difficult to detect and still be detectable if you are sufficiently clever and sufficiently patient. Neutrinos have been detected, their masses have been measured to extraordinary precision, and neutrino astronomy is now a mature field. IceCube at the South Pole, a detector embedded in a cubic kilometer of Antarctic ice, detects high-energy neutrinos from astrophysical sources. CAMLAND in Japan studies reactor antineutrinos and solar neutrinos. The Super Kamiokande detector has watched for neutrinos from supernova explosions. The detection of neutrinos from supernova 1987A 19 neutrinos detected by 3 different detectors in the span of 13 seconds was one of the landmarks of physics in the 20th century. None of this means dark matter will be detected, but it means the non-detection so far is not conclusive proof of non-existence. It means the parameter space has not been fully searched. It means there may be strategies not yet tried, detector technologies not yet invented, energy ranges not yet explored, astrophysical signals not yet recognized. Science has found seemingly undetectable things before. The question is whether dark matter falls into the category of the genuinely undetectable or merely the practically difficult. One distinction matters enormously. Neutrinos interact through the weak nuclear force. They have a finite, calculable cross-section for interaction with ordinary matter. It is just very small. This means detection is in principle possible with large enough targets. If dark matter interacts only through gravity, it is categorically different. Gravity is universal but extraordinarily weak at the particle scale. A dark matter particle interacting only gravitationally with a xenon nucleus would require target masses so enormous and interaction probabilities so small that direct detection would be essentially impossible with any conceivable technology. This is one of the theoretical reasons that the direct detection community has focused almost entirely on dark matter candidates that interact via the weak force. The assumption has been that dark matter must be weakly interacting, not just gravitationally interacting, in order to be detectable. But this assumption could be wrong. Dark matter might interact only gravitationally and be genuinely beyond the reach of any terrestrial experiment. In that case, our only access to its properties would be through cosmological observations, and we would have to accept that we understand the 27% of the universe that is dark matter only in the same way we understand distant galaxies, through the light they affect, rather than through direct laboratory experiments. Part 20. The deepest mystery. Dark energy's unknown nature. Let us return to dark energy because it deserves considerably more than the brief treatment it has received so far, and because it is in some ways even stranger than dark matter. The cosmological constant as a description of dark energy is mathematically clean. You add a term to Einstein's field equations, that term has a specific value that matches observations and the model works. But the cosmological constant as a physical explanation is deeply unsatisfying. It says that empty space has an intrinsic energy density. Fine, but why? What determines the value? Why is it the value it is and not some other value? The theoretical calculation gives something 120 orders of magnitude larger. So why is the observed value so small? This is not just a quantitative puzzle, it is a conceptual puzzle about the nature of empty space. The quantum field theory calculation that fails so dramatically is not a peripheral calculation done under some special assumption. It is the most straightforward application of quantum field theory to the vacuum state. When you quantize a field, you have quantum fluctuations of the field even in the lowest energy state, the vacuum. Each mode of the field contributes to the vacuum energy. Summing all the modes up to some ultraviolet cutoff gives a very large number. The cutoff is chosen at the Planck scale, the scale at which quantum gravity becomes important, and the calculation surely breaks down, but even at much lower cutoffs, the predicted vacuum energy is vastly larger than what is observed. The discrepancy is not an accident of the specific cutoff chosen, it is robust. There are two qualitatively different approaches to this problem. One is to find a mechanism that cancels the large vacuum energy to leave only a small residual. This is called fine-tuning or technical naturalness. No such mechanism has been found. Supersymmetry was once thought to help because it predicts that fermionic and bosonic contributions to the vacuum energy cancel exactly, leaving a vanishing cosmological constant in a supersymmetric universe. But we live in a universe where supersymmetry is broken, and the breaking contributes its own vacuum energy of the wrong magnitude. The cancellation is not exact and the residual is still far too large. The other approach is anthropic. In a landscape of possible universes, each with its own value of the cosmological constant arising from different vacuum configurations of the underlying quantum gravity theory, observers can only exist in universes where the cosmological constant is small enough to allow structure formation. If the cosmological constant were much larger than what we observe, the accelerating expansion would have occurred so early that matter never had time to clump into galaxies. No galaxies means no stars, no planets, no chemistry, no observers. If observers can only exist in universes where the cosmological constant is in a certain range, and if the landscape contains universes with all possible values, then we find ourselves in a universe with a small cosmological constant simply because that is the kind of universe that can be observed. This is the anthropic argument, and it is associated with the string theory landscape, which contains an estimated 10 to the 500th possible vacuum states with different physical constants. The anthropic approach is deeply controversial. Many physicists find it scientifically empty. If every possible universe exists and we are necessarily in the one that allows our existence, then we have not explained anything. We have just described a selection effect. And there is no way to test this framework because we cannot observe the other universes. Critics argue that this is not physics, but metaphysics or even theology in mathematical clothing. Supporters argue that it may be the honest response to a problem that has no conventional solution, and that the landscape may be testable through statistical predictions about other observable quantities. Steven Weinberg made an anthropic prediction before the discovery of the accelerating expansion. He argued in 1987 that the cosmological constant could not be much larger than its observed value because a larger value would have prevented galaxy formation, and he estimated a rough upper bound. When the discovery of the accelerating expansion was made in 1998 and the cosmological constant was measured, its value was within Weinberg's predicted range. Some took this as evidence that the anthropic argument had genuine predictive power. Others noted that the agreement was loose and could not distinguish between the anthropic explanation and some conventional physics that happened to give a small cosmological constant for other reasons. The DESI results suggesting that dark energy may be evolving complicate all of this. If dark energy is not a cosmological constant but a dynamical field, then the anthropic argument applied to a constant value does not apply in the same way. A dynamical dark energy field has its own equations of motion, its own history, and its value today is determined by those dynamics rather than by a fixed constant selected from a landscape. This is in some ways more tractable theoretically because it potentially allows explanations based on the dynamics of specific fields. But it also raises new questions about why the field is rolling at just the right rate to be comparable to the matter density today, a coincidence called the coincidence problem. Why now? Why is the dark energy density comparable to the matter density at precisely the era when observers evolved to measure it? Part 21. What the CMB knows. The cosmic microwave background is the earliest light we can see, the photons released when the universe was 380,000 years old and cooled enough for electrons and protons to combine into neutral hydrogen. Before that moment, the universe was a hot, opaque plasma, and light could not travel freely. After that moment, the universe became transparent, and the photons that had been bouncing around in the plasma streamed freely in all directions. Those photons are still traveling today, and they fill the sky uniformly with a faint glow at a temperature of 2.725 Kelvin. The CMB is not perfectly smooth. It has tiny temperature fluctuations of about 1 part in 100,000, corresponding to the slight density variations in the early plasma. These fluctuations were seeded by quantum fluctuations during inflation, the brief period of exponential expansion thought to have occurred in the first tiny fraction of a second after the Big Bang. The inflationary fluctuations set the initial conditions. Everything that came after, the growth of structures, the formation of galaxies, the evolution of the cosmic web, was determined by those initial conditions and by the physics of the various components of the universe interacting with each other under gravity. The CMB power spectrum, the statistical description of how the temperature fluctuations are distributed across different angular scales on the sky, is exquisitely sensitive to the composition of the universe. The positions, heights, and widths of the acoustic peaks in the power spectrum depend in specific ways on the amount of baryonic matter, the amount of dark matter, the amount of dark energy, and the geometry of the universe. Fitting this spectrum is like solving a system of coupled equations with multiple unknowns where the data provides enough constraints to determine the unknowns precisely. The Planck satellite, launched by the European Space Agency in 2009 and operating through 2013, produced the most precise maps of the CMB ever obtained. Its analysis determined the cosmological parameters to percent-level precision. Ordinary matter is 4.9% of the total. Dark matter is 26.8%. Dark energy is 68.3%. The geometry of the universe is flat to within 0.5%. The Hubble constant is 67.4 kilometers per second per megaparsec. These numbers fit the lambda CDM model with extraordinary precision when applied to the CMB data. The CMB is also full of secondary information that probes later epochs. The integrated Sachs-Wolf effect encodes the effect of dark energy on photons traveling through evolving gravitational potential wells. CMB lensing, the distortion of the CMB by large-scale structure between us and the last scattering surface, probes the total matter distribution, including dark matter, along the line of sight. The Sunyaev-Zeldovich effect, the distortion of CMB photons by the hot gas in galaxy clusters, provides information about the galaxy cluster population, and through that, the matter power spectrum. All of these probes are telling a consistent story. The universe is composed predominantly of dark matter and dark energy in the proportions described. The structures we observe formed under the influence of these dark components, with baryonic matter filling in the gravitational potential wells they created. The entire history of the universe from 380,000 years after the Big Bang to today has been played out within a dark matter and dark energy framework, and the observations match the framework at a level of precision that would have seemed implausible 50 years ago. And yet, as we have discussed, the framework is now under pressure. The Hubble tension is not going away. The matter clustering tension is persistent. The DESI results suggest dark energy may not be constant. The universe is not breaking the lambda CDM model loudly and all at once. It is poking holes in it at the margins, in the precision regime, in the places where the model makes its most specific, quantitative predictions. This is often how physics advances, not through the obvious failure of a theory, but through the accumulation of small, precise discrepancies that eventually demand a new framework. Part 22. The James Webb Space Telescope complication. When the James Webb Space Telescope achieved first light in 2022 and began returning science data, it was expected to extend our view of the early universe and test the lambda CDM model by observing the first galaxies forming in the aftermath of the Big Bang. What it found in the first year of observations has generated considerable discussion in the community. JWST has discovered what appear to be massive, bright, well-formed galaxies at redshifts above 10, corresponding to times when the universe was less than 500 million years old. This is very early in cosmic time. The lambda CDM model predicts that at those early times the universe should still be in the process of building its first galaxies through the hierarchical assembly of smaller structures. The structures observed should be smaller, less massive, and dimmer than what JWST is finding. The galaxies it is seeing are surprisingly large and surprisingly bright for their age. Some are as massive as galaxies in the local universe, formed in a fraction of the available time. This has been described by various researchers with different degrees of alarm. Some say it is already in tension with the standard model. Others say that uncertainties in calibration, in the conversion of observed light to stellar mass, and in the physics of early star formation make it too early to declare a crisis. There may be physics in the early universe that accelerated galaxy formation relative to standard predictions. Early dark energy, if it existed, could have compressed the timeline for structure formation. Alternative dark matter models that allow earlier or more efficient clumping could produce the same effect. The presence of supermassive black holes in the very early universe is a related puzzle. JWST has found evidence for active, supermassive black holes with masses of billions of solar masses in galaxies seen less than 1 billion years after the Big Bang. Supermassive black holes are thought to grow from smaller seeds through accretion of gas and mergers. Growing to billions of solar masses in less than 1 billion years requires extraordinary accretion rates or very massive initial seeds. Neither is easily explained by standard astrophysics. Some proposals invoke dark matter in the formation of the earliest black hole seeds, suggesting that dark matter halos in the early universe facilitated the collapse of gas into massive black holes through channels not available in a purely baryonic scenario. The JWST results are preliminary and under active analysis. They may be resolved by calibration refinements, by a better understanding of early star formation physics, or by revisions to the assumptions made in converting observed light into inferred masses. Or they may represent a genuine tension with the standard model that requires new physics. As of 2025, the community is carefully analyzing several years of JWST data, and the picture is becoming clearer without yet being definitive. Part 23. The Dark Matter Gamma-ray Signal. A detailed examination. The November 2025 gamma-ray result deserves a more careful examination because it illustrates both the promise and the perils of indirect dark matter detection. The signal was detected by researchers at the University of Tokyo, who analyzed gamma-ray observations from a nearby galaxy with the Fermi Gamma-ray Space Telescope and potentially ground-based imaging atmospheric Cherenkov telescopes. The signal showed a spectral feature, a bump in the gamma-ray emission at a specific energy that fits the expected signature of dark matter particles annihilating into lighter standard model particles, which then decay and produce gamma rays. The theoretical picture is straightforward. If dark matter is a WIMP or similar particle that is its own antiparticle, then whenever two dark matter particles collide in a region of high dark matter density, they can annihilate and produce standard model particles. The products of the annihilation depend on what the dark matter particle couples to. If it couples primarily to bottom quarks, then the annihilation produces bottom and antibottom quarks that immediately fragment into jets of pions and other hadrons, some of which decay into gamma rays. The gamma ray spectrum from this process has a characteristic shape, rising to a sharp cutoff at the dark matter mass, which is the maximum energy any individual gamma ray can carry. The signal reported by the Tokyo group is consistent with a dark matter mass in the range of several hundred GeV in the classic WIMP territory, annihilating into bottom quarks with a cross-section comparable to the thermal relic value. If true, this would be the particle mass that explains why there is the right amount of dark matter today. The complication is that every step in this argument involves assumptions. The dark matter density profile in the target galaxy must be assumed because we cannot directly measure it. The astrophysical backgrounds from pulsars, supernova remnants, cosmic ray interactions with molecular gas, and other sources must be modeled and subtracted because they can produce gamma rays with similar spectra. The statistical analysis must be carefully designed to distinguish signal from fluctuations in the background. Each of these steps introduces uncertainty, and each has been a source of controversy in previous dark matter search efforts. The galactic center excess in our own galaxy, the putative dark matter signal in the 2014 Fermi data, has now been studied for over a decade. Recent analyses using data from the Very Energetic Radiation Imaging Telescope Array System, VERITAS, and other ground-based Cherenkov telescopes have not confirmed the dark matter interpretation. The preferred explanation is a population of unresolved millisecond pulsars, dense, rotating neutron stars that produce gamma-ray emission through particle acceleration in their strong magnetic fields. The population is too large and too faint for Fermi to resolve individually, but collectively it produces a diffuse gamma-ray glow that closely mimics what would be expected from dark matter annihilation. The 2025 signal will be tested rigorously over the next year or two. The Cherenkov Telescope Array, CTA, which is in its commissioning phase and will be the most sensitive gamma-ray observatory ever built when complete, will target the same source with far better sensitivity and angular resolution. If the signal is real, CTA will confirm it and provide a much more detailed spectral measurement that can distinguish between dark matter models and astrophysical backgrounds with much higher confidence. If it is astrophysical contamination, CTA will likely reveal the background sources that produce it. The paper has been published in a peer-reviewed journal and has been subjected to community scrutiny. The authors present their case carefully. The community is appropriately skeptical and appropriately interested. The answer will come from more data. Part 24. The anthropic puzzle at the heart of everything. There is a question sitting underneath all of this that science rarely acknowledges openly because it sits at the boundary between physics and philosophy. And it is this: why is the universe configured so that anything interesting can happen? The cosmological constant is the most extreme example of what physicists call fine-tuning, but it is not the only one. The ratio of dark matter to ordinary matter appears to be set at a value that allows galaxies to form but is not so large that gravity collapses everything too quickly into black holes before any stars form. The ratio of dark energy to matter density is comparable today, in the era when intelligent observers have evolved, even though these quantities scale differently with the expansion of the universe and their ratio has changed by many orders of magnitude over cosmic time. This coincidence that we exist at the one epoch when dark matter and dark energy densities are within an order of magnitude of each other is either a remarkable accident or a selection effect, or a clue to some deeper connection. The parameters of the standard model, the masses of the quarks, the strength of the strong force, the mass of the electron, are also suspiciously close to the values required for a chemistry-supporting universe. Small changes to the strong force coupling constant would prevent the formation of carbon in stellar nucleosynthesis. The triple alpha process that produces carbon in red giant cores requires a nuclear resonance in carbon-12 that has to be in just the right place. Change the strong force by even a few percent and carbon production drops catastrophically. Change the electron mass or the proton to electron mass ratio significantly and the chemistry of water and organic molecules breaks down. This collection of apparent coincidences is often discussed under the heading of the anthropic principle, the observation that the universe's physical parameters must be compatible with the existence of observers, because only in such universes would there be observers to notice the parameters. The weak anthropic principle is trivially true but does not explain why the parameters have the values they do. It just explains why we observe the parameters we do, given that we exist. The strong anthropic principle suggests that the universe must have properties that allow the development of observers at some stage, which is a much stronger and more controversial claim that requires a specific framework, like the multiverse, to be well defined. Whether any of this is physics or metaphysics is a genuinely difficult question. It is physics in the sense that it refers to measurable quantities, and makes predictions about what range of parameter values we should expect to observe if the anthropic argument is correct. It is philosophy in the sense that its core claim that all possible universes exist is in principle not testable and requires assumptions about the nature of existence that go beyond what any experiment can access. What is clear is that the 95% problem is entangled with these deeper questions. Whatever dark matter and dark energy are, their amounts are set at values that allow a universe hospitable to complexity. That may be a coincidence, a selection effect, or a clue. We do not currently know which. Part 25. The symmetry argument. Why dark matter might have a dark force. One of the more conceptually appealing directions in dark matter theory is the idea that dark matter is not a single, lonely particle interacting only gravitationally, but rather the visible fraction of a dark sector, a collection of dark particles interacting with each other through their own dark forces in a way that mirrors the structure of the visible sector. The visible sector, our standard model, contains multiple particles interacting through three forces. Photons mediate electromagnetism, gluons mediate the strong force, W and Z bosons mediate the weak force. These forces give the visible sector its richness. Electrons interact electromagnetically. Quarks are bound together by the strong force. The weak force allows radioactive decay. The interplay of these forces and the particles that carry them produces all of chemistry, all of nuclear physics, all of the complexity we see in the visible universe. Why should the dark sector be simpler? There is no theoretical reason to assume it is. Dark matter could equally well be composed of multiple dark particles interacting through dark forces mediated by dark photons or dark Higgs bosons, forming dark atoms and dark molecules, perhaps even a dark chemistry. Such a dark sector would have its own complex structure, potentially including dark stars, dark planets, dark chemistry, and in principle, if the coupling constants and masses worked out right, dark complexity. We cannot observe any of this because the dark sector couples to us only through gravity. But its internal structure would still influence the gravitational imprint it leaves on the visible universe. This is not just theoretical speculation. Specific models of self-interacting dark matter, in which dark matter particles interact with each other through dark forces, have been proposed and tested against observations. Self-interacting dark matter produces density profiles in galaxy halos that are flatter at the center, consistent with the observed cores in dwarf galaxies, because the dark matter particles scatter off each other and thermalize, smoothing out the density cusp. The bullet cluster observation constrains how strong the self-interaction can be, because if dark matter scattered too strongly, it would have slowed down during the cluster collision just as the ordinary matter gas did. The observation that the dark matter passed through without slowing means the interaction cross-section must be below a certain limit. Within that limit, there is room for significant self-interaction. Dark photons are particularly interesting candidates for the mediator of dark sector forces. A dark photon would be a particle with many of the properties of the regular photon, but mixing weakly with the visible photon through a process called kinetic mixing. This mixing allows dark photons to couple to ordinary charged particles at a rate determined by the mixing parameter, which can be very small. Dark photons with appropriate masses and mixing parameters could leave detectable signals in laboratory experiments, particularly through their decay into electron-positron pairs at low masses. The phasor experiment at the LHC, which operates in the far-forward region, where light, dark sector particles produced in proton collisions would appear, and similar experiments at other facilities are searching for these signatures. No signal has been found yet, but the parameter space is being constrained. Dark sector models provide a way to simultaneously address the small-scale structure problems of cold dark matter through self-interaction, maintain consistency with large-scale structure observations, and potentially produce detectable signals that ordinary WIMP models would not. They also suggest that the 95% of invisible universe may be far more complex and structured than we have assumed. The simplest dark matter model is a single particle interacting only gravitationally. The most physically motivated dark matter model, if we take the visible sector as a guide, is a rich dark sector with multiple particles, multiple forces, and complex interactions whose observable consequences we have only begun to explore. Part 26. The dark sector and the fifth force. There is a class of models that goes even further, suggesting that dark matter interacts with ordinary matter, not just through gravity, but through a fifth force, a new, fundamental interaction beyond the four we know. This interaction would be very weak at the scales of ordinary particle physics experiments, which is why it has not been detected, but could be significant at the scales of galaxies and galaxy clusters, providing an additional connection between the dark and visible sectors. Such a fifth force might be mediated by a scalar or vector boson with a mass that determines the range of the interaction. A very light mediator would produce a long-range force felt across galactic scales. A heavier mediator would produce a shorter-range interaction relevant only at shorter distances. The interaction could be constrained by the same strong equivalence principle tests that constrain any additional gravitational-like interaction, by searches for fifth force signals in Earth-based precision experiments, and by astrophysical observations of the dynamics of galaxy clusters and binary pulsar systems. Emerging gravity, Verlinde's 2016 proposal, can be viewed in this framework as a version of a fifth force arising from the quantum information content of the dark energy medium. The force it predicts is attractive and scales in a specific way with the ordinary matter distribution in a manner that reproduces Mund-like behavior in galaxies while being consistent with larger-scale observations. The observational tests of this framework are ongoing and the results are mixed. The key point is that the concept of dark energy coupling to ordinary matter through something other than gravity is physically possible and potentially observable. If dark energy has any coupling beyond gravity, it would show up as a time variation of fundamental constants, as anomalous accelerations on small scales, or as deviations from the predictions of general relativity in precision tests. No such signal has been confirmed, but the parameter space is large and many regions remain unexplored. The interactions between the dark and visible sectors are ultimately an empirical question. We are building more precise instruments, developing more creative analysis methods, and searching in more corners of parameter space. The answer, when it comes, will tell us whether the dark universe is truly isolated from us except through gravity, or whether there is a portal, however small, connecting the two sectors and allowing us to eventually understand both. Part 27. Cosmological Simulation and the Next Generation. The field of cosmological simulation has advanced to a point where it has become one of the primary tools for understanding the dark universe. The difference between simulation and observation is profound, but their interplay has driven enormous progress. Simulations make predictions, observations test them. Discrepancies between simulations and observations point to missing physics, errors in the observations, or both. The illustrious TNG simulations run on supercomputers at the Max Planck Society and elsewhere, model volumes of the universe hundreds of megaparsecs across with full magnetohydrodynamics, star formation, stellar feedback, black hole growth and feedback, and cold, dark matter gravitational dynamics. The simulations produce synthetic universes that can be compared directly with observed galaxy populations, galaxy morphologies, galaxy clustering statistics, and the distribution of gas in and around galaxies. The agreement is remarkable in many respects and informative in its failures. The Flamingo simulation, completed in 2023, is the largest hydrodynamic cosmological simulation ever run, modeling a volume about 1 billion light-years across. It was designed specifically to study the effects of baryon physics on the matter-power spectrum, because these effects are important for interpreting weak lensing surveys like Euclid and Rubin. The simulation shows that the jets and winds from active galactic nuclei, the supermassive black holes at the centers of galaxies that become active when they accrete gas, can redistribute gas and suppress the formation of structures on scales of tens of megaparsecs, significantly modifying the matter-power spectrum at scales relevant to weak lensing surveys. Without accounting for these effects, the comparison between simulated and observed matter-power spectra would be misleading. The next generation of simulations is being designed to address the interface between dark matter physics and baryonic physics more carefully, to test specific dark matter particle models with different self-interaction strengths and different velocity dispersions, and to predict the observable signatures of those models in the rich datasets being produced by Euclid, Rubin, DESI, and SCIA. The challenge is that the parameter space of dark matter models is vast, and the computational cost of high-resolution simulations is enormous. Machine learning methods, including neural networks trained on simulation outputs, are being developed to interpolate between simulation results and accelerate the comparison with observations. These methods allow exploration of far larger parameter spaces than direct simulation could reach. The future of dark matter research is increasingly data-driven. The observational datasets being produced in this decade are larger and richer than anything that has come before. The theoretical tools for interpreting them are more sophisticated. The computational resources for running simulations and comparing them with data are more powerful. The combination may be what finally moves the dark matter question from the category of profound mystery to the category of something we understand well enough to test with precision, not necessarily knowing what the particles are, but knowing their properties and behaviors well enough to begin to discriminate among the theoretical candidates. Part 28. The Particle Physics Frontier. Everything we have discussed so far about dark matter candidates has been in the context of existing theoretical frameworks: WIMPs from supersymmetry, axions from Pecci-Quinn symmetry, sterile neutrinos from neutrino mass models. But particle physics has a history of finding particles not anticipated by any existing framework. The tau neutrino was discovered decades after its existence was predicted. The top quark turned out to be much heavier than expected. The Higgs boson was the last piece of the Standard Model, and its discovery completed a framework. But every theoretical physicist knows the Standard Model is incomplete. It has too many free parameters, it does not include gravity, it does not explain the matter-antimatter asymmetry of the universe, and it does not explain dark matter or dark energy. These are all signals that new physics exists beyond the Standard Model. Several theoretical frameworks beyond the Standard Model have been proposed that contain dark matter candidates not included in the ones we have discussed. Twin Higgs models, in which the Standard Model is paired with a mirror copy of itself that solves a naturalness problem and contains hidden sector particles that serve as dark matter. Extra dimension models, in which Kaluza-Klein excitations of gravitons or other particles propagate in the bulk of extra dimensions and appear as massive, neutral particles from the four-dimensional perspective. Asymmetric dark matter models, in which the relic abundance of dark matter is set not by annihilation, but by an asymmetry between dark matter and anti-dark matter, analogous to the baryon-antibaryon asymmetry of the visible universe. These models naturally connect the dark matter relic density to the baryon density and can explain why they are in the same ballpark. The Large Hadron Collider has not found any of these, but its full dataset has not yet been fully analyzed, and its run continues. The next generation of colliders being considered, the future circular collider at CERN, which would be a 100-kilometer ring reaching energies of 100 TeV, or the proposed International Linear Collider, would explore new energy frontiers where some of these heavier, dark matter candidates might appear. The timeline for these machines is long, well into the second half of this century, but the science case is strong. In the meantime, the most immediate hope for a dark matter particle identification may come from indirect detection. The Cherenkov telescope array, in its full configuration with dozens of telescopes across 2 sites in the Canary Islands and Chile, will have an order of magnitude better sensitivity than existing ground-based gamma-ray telescopes. It will be able to probe dark matter annihilation cross-sections down to the thermal relic value across the entire WIMP mass range from a few hundred GeV to a few hundred TeV. If WIMPs exist in this mass range, CTA will likely see a signal. If CTA sees nothing, it will effectively rule out most of the standard WIMP parameter space. Either outcome is scientifically valuable. For axions, several next-generation experiments are being designed. Abra-10L, AION, and the proposed MAGIS experiment are based on atom interferometry and are sensitive to axion-like dark matter through its effect on atomic transitions. BEAST, the broadband resonant approach to cosmic axion searches with time-varying systems, uses a broadband approach to cover a wider mass range more efficiently. The Cosmic Axion Spin Precession Experiment, CASPER, uses nuclear magnetic resonance techniques to search for axions through their coupling to nuclear spins. The proliferation of axion search techniques is a healthy sign that the community is taking seriously the possibility that the answer is in this part of parameter space. Part 29. When did the dark universe begin? One of the deepest questions about dark matter and dark energy is not what they are now, but when they appeared and how they influenced the early universe. This is not just a historical curiosity. The history of dark matter and dark energy is encoded in the observations we can make today, and reading that history correctly may provide clues about their fundamental nature. Dark matter, in the standard cold dark matter picture, was present from the very earliest times accessible to cosmology. In the standard lambda CDM model, dark matter decoupled from ordinary matter in the very early universe, before Big Bang nucleosynthesis, and has been evolving only under gravity ever since. It began forming halos as soon as density perturbations grew large enough to become gravitationally bound, which happened at different times for different mass scales. Small halos formed first, then merged into larger ones, bottom-up structure formation. The first dark matter halos may have formed as early as a few 100 million years after the Big Bang, providing the seeds for the first galaxies and the first stars. The epoch of rayonization, roughly between 300 and 900 million years after the Big Bang, is a particularly important window into the dark universe. This is when the first stars and galaxies formed and began ionizing the neutral hydrogen that filled the universe. The timing and morphology of reionization depend on the dark matter halo population. Small dark matter halos host the first galaxies, which are the sources of ionizing radiation. The abundance and clustering of these small halos is sensitive to dark matter properties. Warm dark matter with masses of a few kilo-electron-volts would suppress the formation of the smallest halos and delay the onset of rayonization. Fuzzy dark matter would have similar effects, but through a different mechanism. The 21 centimeter signal from neutral hydrogen during and after rayonization, which SKA will be able to map, is a direct probe of this epoch and of the dark matter properties that shaped it. Dark energy's early history is less clear. In the standard lambda CDM model, the cosmological constant has been present since the beginning, but its effect was negligible in the early universe when matter density was much higher. The universe transitioned from matter-dominated to dark, energy-dominated expansion only within the last few billion years. But if dark energy is evolving, its history before this transition may have been different. Early dark energy models proposed that there was a significant dark energy component in the early universe before recombination, which would leave a distinctive imprint on the CMB and on the growth of structure. The Hubble tension may in fact be telling us that early dark energy was present and modified the pre-recombination expansion history. The specific form of early dark energy that best fits the data is being actively debated. Models tied to ultralight axion particles, where the dark energy at early times is associated with an axion field that was briefly relevant before decaying away, have been studied extensively. These models can reduce the Hubble tension significantly, though not entirely. They make predictions for the CMB power spectrum and for structure growth that are being tested with increasingly precise data from the Atacama Cosmology Telescope and other instruments. Part 30. The Philosophical Revision. What does invisible mean? We began this journey with the claim that 95% of the universe is invisible, and we have spent considerable time unpacking the evidence and the implications of that claim. But as we near the end, it is worth reflecting on what invisible actually means in this context, and whether the framing itself reveals something important about the limits of human cognition as a scientific instrument. Invisible to what? To eyes, to the specific biological photoreceptors in the human retina that evolved to detect electromagnetic radiation in a narrow band between roughly 400 and 700 nanometers of wavelength, the visible spectrum. This is an extraordinarily narrow slice of the electromagnetic spectrum, which extends from gamma rays at wavelengths smaller than atomic nuclei to radio waves with wavelengths of kilometers and beyond. Human eyes can detect only this tiny sliver, and only because the sun emits most of its energy in this range, and terrestrial evolution selected for sensitivity to the ambient light. The universe has always been far richer in electromagnetic radiation than the visible spectrum captures. Astronomers learned this in the 20th century as they built instruments sensitive to X-rays, ultraviolet, infrared, radio, and gamma rays. The invisible universe of X-ray astronomy revealed black holes and neutron stars and the hot intracluster medium of galaxy clusters. The invisible universe of radio astronomy revealed pulsars, cosmic microwave background radiation, and the 21-centimeter emission of neutral hydrogen that maps the distribution of gas across the galaxy. The invisible universe of infrared astronomy revealed star formation hidden behind dust clouds. Each expansion of the electromagnetic window into the universe revealed a new layer of reality that eyes alone could never see. Dark matter and dark energy are invisible in a deeper sense, not invisible to human eyes, but visible to the right telescope in the wrong spectrum. They are invisible to all electromagnetic detection because they do not interact with the electromagnetic field at all, or do so at levels far too faint for any detector we have built. They can only be detected gravitationally through their effects on the motions of things that do emit light, or through the warping of space-time that allows us to measure their mass without seeing them directly. This is a genuinely different kind of invisibility, not a matter of needing a bigger telescope or a different wavelength. A matter of the fundamental physical coupling between dark matter and the force through which all of our observational instruments ultimately work. This invisibility is a reminder that the universe is not obligated to be visible to us. Our senses and the instruments we build to extend them detect phenomena that couple to the electromagnetic force or to gravity. Our entire history of scientific observation has been the history of detecting things that interact with electromagnetism or gravity. The standard model of particle physics is, in a deep sense, a theory of electromagnetic and nuclear interactions with gravity added separately. We know how to build detectors for photons, for electrons, for protons, for the particles of the standard model. We do not know how to build detectors for particles that interact only gravitationally. We know from experiment that such detectors must be sensitive to gravitational effects alone, and gravitational effects alone at the particle scale are extraordinarily faint. The question of whether dark matter and dark energy will ever be accessible to direct detection, whether they will remain in the category of things known only by their effects on visible matter, is ultimately a question about whether the dark sector has any coupling to the visible sector beyond gravity. If it does, detection is possible. If it does not, we may be permanently restricted to indirect evidence. The answer to that question is not yet known, and how we proceed in the search depends critically on the answer. The current generation of experiments is based on the assumption that there is some non-gravitational coupling, that dark matter particles interact with ordinary matter through at least the weak force. If that assumption is wrong, the entire paradigm of direct detection is misguided. Part 31. The possibility we are not asking the right question. There is a humbling precedent in the history of physics for the situation we are in. In the 19th century, physicists were trying to understand the properties of light. They knew light was a wave. They knew waves needed a medium. Sound waves need air. Ocean waves need water. Light waves, they assumed, needed a medium too, and they called it the luminiferous ether. The ether was invisible, of course, and you could not directly detect it. But if it existed, you should be able to detect Earth's motion through it, because Earth moves around the Sun at 30 kilometers per second and should be moving through the ether. The Michelson-Morley experiment in 1887, with extraordinary precision, measured the motion of Earth through the ether. It found nothing. The ether did not create a measurable drag. The measurement was null. For decades, physicists tried to explain this null result within the framework of the ether hypothesis. They added properties to the ether that would cause it to hide. Lorentz proposed that objects contracted in the direction of motion through the ether, which would explain why the detection apparatus could not measure the Earth's motion. The modifications became increasingly baroque. Then Einstein proposed special relativity, which abandoned the ether concept entirely. Light did not need a medium. Light was a self-propagating electromagnetic wave that traveled at a constant speed in all reference frames, and this constancy, rather than an ether, was the fundamental fact from which all the observations could be derived. The solution to the problem was not to add more properties to the ether. It was to realize that the ether was the wrong concept entirely. The dark matter situation may be analogous. We have been looking for a particle that fits into the existing particle physics framework, that couples to the standard model through known forces, and that can be detected by instruments designed on the principles of the standard model. The experiments have found nothing. We have responded by ruling out parameter space, proposing modifications to the models, and building more sensitive versions of the same experiments. But it is worth entertaining the possibility that the entire framework is wrong. That dark matter is not a particle in the standard model sense, that the modifications of gravity needed to explain the rotation curves, however awkward and incomplete, are pointing at something real, that the cosmological constant problem is pointing at a deep misunderstanding of quantum gravity, that the next revolution in physics will not find the dark matter particle, but will instead find a new framework that makes the question look different from the inside. This is genuinely uncertain territory. We are not in a position to know whether the standard picture of dark matter as particles needs to be replaced by something fundamentally different. The evidence for dark matter, from rotation curves, from the CMB, from the bullet cluster, from structure formation, is compelling. It points strongly at the existence of a substance with mass that does not interact electromagnetically. That evidence does not go away if we reframe the question. Whatever the new framework is, it must account for all the same data. But how it accounts for it, and what that implies for detection, may be completely different from what current experiments are designed to find. The most honest position is the one that keeps both possibilities genuinely open. Dark matter might be found by the next generation of direct detection experiments, or by CTA, or by some future collider. Or it might be that a theoretical revolution is needed first, one that we cannot currently see coming, and that will reframe the problem in a way that makes the solution seem obvious in retrospect. Part 32. What comes next? The next decade of cosmology and particle physics is the richest experimental program in the history of the field. Multiple major instruments are either operating, being completed, or in early science phases simultaneously. The combination of their data will constrain the dark universe with greater precision than any previous era. The Vera C. Rubin Observatory has begun its legacy survey of space and time, a 10-year program that will image the entire accessible southern sky roughly every few nights in multiple wavelengths. Over 10 years, it will detect approximately 17 billion galaxies, measure the shapes of 3 billion with sufficient precision for weak lensing, discover over 1 million type Ia supernova, find thousands of new, strong gravitational lensing systems, and catalogue an enormous population of new solar system objects, including many that will help constrain the properties of the outer solar system. For dark matter, the weak lensing maps will constrain the matter power spectrum and galaxy halo connection to unprecedented precision. For dark energy, the supernova survey will extend the distance redshift relation to higher redshifts than any previous survey and test whether dark energy evolution is consistent with the hints from DESI. The DESI survey is continuing to accumulate data. Its final data set, expected to cover tens of millions of galaxies across a large fraction of the sky, will provide the most precise baryon acoustic oscillation measurements ever made, constraining the cosmic expansion history across the full range of redshifts accessible to spectroscopic galaxy surveys. The hints of evolving dark energy will either solidify into a discovery or be revealed as a statistical fluctuation by the end of the DESI program. Euclid is producing weak gravitational lensing maps of the northern sky from space, with its clean point spread function uncorrupted by atmospheric distortions. Its combination with Rubin's southern sky coverage will eventually give us full, sky-weak lensing maps that constrain dark energy and dark matter simultaneously. The Nancy Grace Roman Space Telescope, expected to launch in the late 2020s, will conduct a wide-field infrared survey combining supernova cosmology, weak gravitational lensing, galaxy clustering, and microlensing surveys in a single instrument with Hubble quality resolution over a field of view 100 times larger than Hubble's. Its microlensing survey toward the galactic bulge will constrain the population of compact objects in the dark matter halo, and its supernova survey will extend the distance redshift relation to the highest redshifts ever probed in the infrared. The Simons Observatory, currently being commissioned in the Atacama Desert in Chile, and its planned successor, the CMB-S4 experiment, will measure the polarization of the cosmic microwave background to levels that probe the faint imprint of primordial gravitational waves, constrain neutrino properties, and test early dark energy models. The detection of CMB-B mode polarization from primordial gravitational waves would confirm the inflationary paradigm and provide direct constraints on the energy scale of inflation. The SKA, when its full array is operational, will map neutral hydrogen across cosmic time and test the matter power spectrum on scales from intergalactic filaments to the largest structures in the universe. It will detect thousands of new pulsars that can be used as gravitational wave detectors, and its pulsar timing array data will complement LIGO in the gravitational wave window into dark matter and dark energy. All of these experiments will generate petabytes of data that will require the most sophisticated analysis tools ever applied to astrophysics: machine learning, Bayesian inference, neural network emulators, simulation-based inference. These are the computational tools being developed to extract the maximum cosmological information from the next decade of observations. The collaboration between observational astrophysics, theoretical cosmology, and data science has never been more productive. Part 33. If we never find it. Before we close, we should sit honestly with a possibility that is uncomfortable but scientifically legitimate. What if we never find dark matter in any direct detection experiment? What if every successive generation of more sensitive instruments finds nothing? What if the Axion search covers the full, theoretically motivated parameter space and comes up empty? What if the WIMP cross-section limits continue to be pushed lower and lower with no signal? What if the gamma-ray searches and the gravitational wave searches and the supernova surveys constrain dark energy to be consistent with a cosmological constant with no hint of dynamics? It would not mean that dark matter and dark energy do not exist. The evidence for their existence through their gravitational effects is not going away. The flat rotation curves will still be flat. The CMB will still require dark matter to explain its pattern. Large-scale structure will still require dark matter scaffolding to explain its formation. The universe will still be accelerating in its expansion. What it would mean is that we are in the situation of the neutrino before the reactor experiments. We would know that something exists, we would know roughly how much of it there is and how it is distributed. We would know many of its large-scale properties, but we would have no direct particle identification. We would be in the position of knowing the mass of an element before being able to identify its atomic structure. Not nothing, but not complete. There is a form of cosmology that deals with this situation. It is called effective field theory applied to cosmology, and it treats the dark matter and dark energy components as fluids with certain properties, equations of state, sound speeds, clustering behaviors, without committing to a specific particle physics model for what they are made of. Observational data can constrain the properties of the dark fluid without revealing its fundamental constituents. This is not satisfying to a particle physicist who wants to know the Lagrangian, but it is progress of a sort, and it is what we may have to accept if the direct detection frontier continues to return silence. The situation with dark energy is potentially even more intractable. Dark energy may be the energy of the vacuum, and if so, understanding it requires a theory of quantum gravity that does not yet exist. We may be able to measure its evolution precisely with DESI and Rubin and Roman, constrain its equation of state to high precision, and still not understand what it is at a fundamental level, because the fundamental answer lies in the regime where quantum mechanics and gravity overlap, and we have no confirmed theory of that regime. This is where the story of the 95% finds its most honest resting point. Not in a neat resolution, not in a missing piece found and fitted into place, but in a clear articulation of how deep the mystery goes, how many different directions lead to the same question, and how the question connects, at its roots, to the deepest unsolved problems in all of theoretical physics. The incompatibility of quantum mechanics and general relativity, the nature of the quantum vacuum, the origin of the initial conditions of the universe, the relationship between the dark and visible sectors. These are not peripheral problems being picked at by specialists. They are the central problems of physics, and the 95% problem is one of the clearest empirical expressions of their depth. Part 34. The dark universe and what it means to know. There is a habit in science communication of presenting the unknown as a gap to be filled, a puzzle with a missing piece waiting to be found. The dark universe invites a more honest framing. It is not a gap in the known. It is a shadow cast by the limits of the framework, and the shadow is very large. When you look up at the night sky and see the stars, you are seeing the lit portions of a universe that is mostly dark. Not dark as in unilluminated, dark as in made of something that produces no light and cannot be detected by anything in your field of view. The stars you see represent a fraction of the matter in their own galaxies. The dark matter halos surrounding those galaxies are more massive by far and invisible in any conventional sense. The space between the galaxies is not empty. It is filled with diffuse hot gas with the warm, hot intergalactic medium and pervaded by the dark energy of the vacuum. The entire visual field, everything that appears bright and structured and comprehensible, is the lit surface of an ocean whose depths are something else entirely. The cosmic web is more accurately called the dark cosmic web. The luminous galaxies and quasars and gas clouds that we map are tracers of a dark matter distribution that they themselves do not define. The dark matter filaments, sheets, and halos were there first, and the ordinary matter fell into them and lit up where the gravity was concentrated. Every galaxy is a lit island in a dark sea. Every galaxy cluster is a crowded archipelago in the same dark sea. The sea is 95% of everything, and we have been studying the islands and calling that the universe. This reframing matters not just poetically, but scientifically. It means that the universe we have built our entire cosmological framework around, the universe of atoms and photons and electromagnetic interactions that has been the subject of physics since Galileo pointed his telescope at the sky, is a minority component of what exists. It is the part that is accessible to our kind of observation. The majority is accessible only through gravity or potentially through new physics we have not yet discovered, or potentially not at all. Humans are built of atoms. Our instruments are built of atoms. The phenomena our instruments are designed to detect are phenomena that involve atoms interacting with photons. We are, in a very literal sense, part of the 5%, looking at the 5% through instruments made of the 5%, and trying to understand the other 95% that surrounds and pervades us. The mismatch between the observer and the observed has never been more stark or more interesting. Part 35, the conclusion that holds open rather than closes. Science, in its most rigorous form, is not about arriving at certainty. It is about arriving at better questions. The 95% problem has given physics better questions than almost anything else in the past century. Not just what is dark matter or what is dark energy, but what is the true nature of gravity on cosmic scales? What is the quantum nature of space-time? What determines the initial conditions of the universe? How does the dark sector couple to the visible sector? And what frameworks are needed to think coherently about a universe in which most of what exists is categorically different from what we observe? Those questions are not rhetorical, they are active research programs. They are being attacked by thousands of physicists on 6 continents using instruments from underground cryogenic detectors to space telescopes to 100-kilometer colliders to gravitational wave observatories to radio arrays. The attack is relentless and increasingly sophisticated. The data being generated in this decade is the richest in the history of cosmological observation. The theoretical tools for interpreting it are the most powerful ever developed. And the answers are not here yet. The 95% is still 95%. Dark matter has not been detected in any laboratory. Dark energy has not been understood at any fundamental level. The Hubble tension persists. The DESI hints of evolving dark energy are real, but not yet confirmed at discovery threshold. The JWST anomalies are real, but not yet resolved. The gamma-ray signal from the Tokyo group is intriguing, but not yet confirmed. The current moment in cosmology is one of mounting evidence and deepening puzzle, not approaching resolution. We are richer in constraints than in answers. What you take away from sitting with this for 3 hours should not be despair or nihilism about the limits of human knowledge. It should be the opposite. The fact that 95% of the universe is made of something we cannot see, that we know this with extraordinary precision, that we have mapped its effects across the entire history of the cosmos, that we have built instruments of astonishing sensitivity searching for its particle manifestations, that we have a dozen serious theoretical candidates and none of them confirmed, that the problem connects simultaneously to the deepest puzzles in quantum mechanics, general relativity, and cosmology. All of this is not evidence of failure. It is evidence of how far our curiosity has reached. We are, as far as we know, the only part of the visible universe that can ask these questions. The dark matter in the halo of the Milky Way does not wonder what it is. The dark energy of the vacuum does not contemplate its own nature. Whatever dark sector particles exist, they have no science. The 5% of the universe made of atoms, and specifically the extraordinary subset of those atoms arranged into nervous systems capable of theoretical reasoning, is the only part of the universe doing what we are doing right now. Trying to understand the whole from the inside, that project is unfinished. It may always be unfinished in some respects because the universe has no obligation to be comprehensible to the organisms that evolved on one of its minor planets, but the attempt is what distinguishes the lit portion of the universe from the dark portion, not the matter, because matter is matter in both sectors. The attempt is what matters, the asking of the question. What is in the 95%? We do not know. We know it is massive, dark, and pervading. We know it is necessary for the universe we can see to have formed the way it did. We know it is determining the fate of every galaxy and the ultimate destiny of the cosmos. We know it is passing through us right now, through the room you are sitting in, through the atoms of your body, undetected and undetectable by any current instrument. We know that understanding it is one of the great remaining challenges of our species. And we know that somewhere in the mathematics we are writing, in the data we are collecting, in the theoretical frameworks we are building, the answer is waiting, not yet visible, but there, in the same way that dark matter is there, invisible and present, shaping everything we can see, waiting to be read by whoever is patient and brilliant and lucky enough to find the right way to look. The universe is mostly dark. That is the fact from which everything in this conversation has proceeded. And the most honest thing that can be said in reply to that fact is not an explanation and not a dismissal. It is a question. The same one physicists have been asking for 90 years in different languages and with increasingly sophisticated tools. The question is simple. What is it? And the universe, patient and indifferent and full of dark energy pushing it apart at an accelerating rate, has not answered yet. But somewhere in the light that reaches us from across 14 billion years, in the subtle distortions of a billion galaxy shapes, in the quiet null results of buried xenon tanks, in the flat rotation curves of 1,000 spiral galaxies, in the CMB photons that have been traveling since before there were any stars, the answer is encoded. We just need to learn to read it. And that is what physics is doing right now, on every continent, in every time zone, in every language, working carefully and systematically toward the thing the universe is hiding from us. Not because it is shy, because it is large, and we are still learning what large means. If this is the kind of conversation you want to have at night when the world goes quiet, subscribe and come back. There is more universe than any of us can hold in our heads, and we are going to look at as much of it as we can, together, for as long as the stars keep burning.